Loftin. It's nice to meet you guys, both online and in person. I am the KSC University Relations Manager here. And Brian's asked me to give you an introduction. Just wanted to welcome you to KSC. It's such a fun time to be here. Okay. So I'm going to do a little bit of a welcome, then I'm going to introduce you guys to some of the KSC research and technology here, and then talk about some student opportunities. Okay. See if we can get this video to start. It's not showing. All right. It was an exciting time to be here. I hope a lot of you got a chance to see what was going on online and hear the volume. In our room, we didn't get to see it, but this was like a magical moment, the pinnacle of many of our careers. So it's just a fun time to be here. I just wanted to give you guys a little bit of fun stuff before I went on to the next one. Okay. So KSC's R&T community. At KSC, we do quite a bit of research around here, even though you think of us as a launch provider. We also do research and technology. We are launching payloads, scientific payloads for exploration. We're also sending payloads up to the International Space Station. And the areas that Kennedy Space Center does research in is in crop production, that's plants as food for the astronauts for long duration missions, dust mitigation. I'll go through some of these a little bit more. We call it E-Class life support, in situ reutilization, in space and surface systems. That's something near and dear to your hearts. Ground systems, scientific instrumentation, and waste management. So I wanted to do just a little bit of dive into plant food production. We do this here because in long duration missions, taking all the astronauts' food is not a really good idea because they start to lose nutrients. So we realized that we're going to have to grow some fresh plants to provide those nutrients. So we do a lot of that work over here at KSC. If you guys are interested in it, I'm trying to go fast, so. We do dust mitigation on the moon and the lunar surface and the Martian surface. There's dust everywhere, and the electrostatic properties are a huge concern. There is no atmosphere, so we have to work to getting dust off of all of our like solar arrays and some of our cameras and stuff. So we do some technology there that's set to the moon on Eclipse missions for that. In situ reutilization. This is what we call living off the land. Once we get to the moon, we need to use as many of the resources that are there to be able to stay for a long time. So what we do here is we do a lot of testing of, we look for volatiles for water. We look at using the regolith to break it down to the metals and the oxygen. We like to see that as Lewis and Clark because when they crossed over the nation, they weren't able to bring everything with them. So you have to learn how to live off the land. So in situ reutilization is something we do a lot here at KSC. We also do in-space and surface systems. This is a picture of the Viper rover. At KSC, we developed one of the instruments, the MSOO mass spectrometer that's on here. This manifested mission will be going to the moon to look for water. We've got a neutron spectrometer looking in there, a near infrared spectrometer, a drill, and our mass spectrometer. As I mentioned, scientific instrumentation for exploration. What KSC is really good is taking commercial off-the-shelf instruments that have a terrestrial use and ruggedizing them and sending them off to space. So this is just an example of one of the main instruments that we worked on. Amy's done quite a bit here as well. Okay, so that's all I wanted to talk to you about the research that we're doing here. There's so much more, but I just wanted to give you guys an introduction to everything. And Brian said you guys might want to look at student opportunities here. I'll be sharing my slides, and all of them have links. Internships at Pathways. The 26th deadline is May 12th. We really suggest you apply for those if you want to. We also have Pathways. It's a type of internship that's kind of more like a co-op program where you take a semester off and you go in and you take a semester off. That's a little bit more of a guiding way to get you as a civil servant employment. We also have fellowships. When you guys get this message, you can click the links for it, and JPL internships. And that's it for me. I just wanted to welcome you to KSC. Thank you for coming here. And if you guys have any questions, my email will be on the slides.
Okay. So yeah, I didn't really give an intro of who I am. So my name is Brian Newfer, for those who can see me online. We had some snafus and badging, but sorry about the delay. Still have two trying to get through, but I think I figured out. So Amy and I are kind of unique at KSC. We work in space propellant transfer R&D, and we mainly support Goddard and JSC type missions that are going out of there. So yeah, so we've had a lot of fun here. So we don't want to delay anymore. So do you want to go ahead and get rolling on the presentations? The first team, Jacob, Rachel?
Sure. Yeah. Like Rachel will pull up the first briefing. We'll have them start at 8:30. This is this is the space rats are going to kick us off. So I see some of the teammates are on here. So yeah, we try to stay on schedule as much as possible, but we're 15 minutes delay. So we'll try to keep to that delay. So once the clock hits 8:30, you guys can go ahead and start rolling. And Rachel, are you recording?
Yes, we are recording.
Okay. Yeah, and I guess since I have a minute here, I will say it's been good. You know, like we've reached the halfway mark. I'm really proud of the work all the teams have done. I saw some great stuff yesterday. I know we'll see some more great stuff today. Um, Next year, you know, like if there's professors and mentors here, we're doing it again. Like we've already opened signups. We're going to add a track for in space to return to Earth through dispatch space. Highly encourage the students to submit to SciTech or other conference publications. We kind of push in that direction, and you know anyone there probably heard about it, but obviously NASA has Ignition. There's an RFI out now about doing things on the moon with payloads. You know, both track one and track two, a lot of those could fit right in there. So if you have any questions, ask me if you want more details, but otherwise I will turn it over to the rats in space.
All right, can you hear me?
Yes.
All right, cool. Well, if there's nothing else, we can get started. Um, Hello, everyone. Welcome to our final showcase for the Track 1 manufacturing. My name is Aiden Tamofti, and I'm joined by Oliver Robeg Perez, Lily Mikolas, Hirokuni Kakauchi, and James Glynn, and we are Rats in Space. I'd like to thank our primary advisor, Dr. Manoranjan Maji at Texas A&M, and also thank our C3 mentor, Dr. Jacob Rome. Next slide. So starting with the executive summary, spacecraft component production on Earth is becoming inefficient for modern mission needs, both in weight and size. And the idea of in-space servicing, assembly, and manufacturing is becoming increasingly popular. Specifically, ISAM enables on-orbit construction and repair of spacecraft, manufacturing parts in space for said spacecraft, and consistent maintenance and upgrades without the need to return to Earth. Our mission focuses on manufacturing of carbon fiber tubes in space for eventual structural and commercial use without the need to manufacture on Earth. Next slide. So just to go over our project management milestones, in September of last year, we selected a program manager and began development. We chose our operations and capabilities as well as defined our requirements in October. We also completed our trade studies in October. And in late October, we finalized our conceptual design. And the past couple months, we have been working on that design, fixing kinks, and generally refining it for PDR. Next slide. So to talk about feasibility for a minute, we believe that the proposed design is highly feasible and that we designed this project for immediate implementation with many commercial off-the-shelf parts. Space rating will need to be done in-house, and this was deemed much simpler and far cheaper than ordering space and launch-rated parts individually. There's no additional risk introduced in this, as testing the entire system instead of piecewise rating still satisfies NASA's requirements, and we think it'll mitigate risk while also keeping this at a very low budget overall. Next slide. So we also think that this is a pretty high value mission. It contributes to manufacturing in space, and specifically, we are working towards breaking Earth constraints. Current launch capabilities are limited in weight and size, specifically diameter of the launch vehicle, and that places a hard cap on the scale of space infrastructure. And we hope that this conceptual design can bridge the gap to enable next generation exploration and provide the foundation for constructing advanced systems that cannot be launched from Earth, which includes nuclear electric propulsion drives, large structural trusses, and to that end, large-scale orbital habitats. Next slide, please. So,
Hi.
oh yes, and now for Hiro, he's going to talk about data handling.
Here, I'll walk through our data handling and communication architecture. Our system is designed to operate semi-autonomously, meaning it does not rely on continuous ground control. The operator is mainly involved for high-level actions, like starting or stopping the process, monitoring system health, and issuing emergency overrides if needed. From a reliability standpoint, the system can fully execute the manufacturing sequence on its own. If something goes wrong, We have both automatic shutdowns triggered by sensitive thresholds and manual emergency stop capability with about 2 seconds response time. Importantly, the system is designed to continue operating safely even during temporary communication loss. On the communication side, downlink is split into 2 parts. Low rate continuous telemetry, at least 1 kilobit per second for system health data, and high rate burst transmission around 3 megabits per second for video. This allows us to verify operations and detect anomalies. Uplink requirements are minimal, under 1 kilobit per second, since we're only sending simple commands like start, pause, and emergency stop. We also log at least 30 days of data on board to ensure no data is lost. Next slide, please.
Right. So talking about innovative concepts, we think that there's 3 main things that our design innovates on. The big thing is that we are using a novel method of carbon fiber composite manufacturing called frontal polymerization. It utilizes a special resin composed of this chemical called dicyclopentadiene, or DCPD, and it allows for curing of carbon fiber composites with lower thermal requirements, making it more feasible for in-space usage where autoclaves or high temperature environments are not amenable to the design. We also have made some innovations in microgravity resin application, which needs special attention to avoid bubbles and other manufacturing defects. The plunger design of our resin storage chamber contributes to mitigating this. And we also have designed a self-winding mandrel using a jam cleat geometry, which contributes to low waste, rapid winding of fiber that can be applied to general spooling processes. Next slide, please. We also identified some technology gaps that, if addressed, would make the design much more feasible and easy. In-vacuum epoxy curing would remove the need for a pressurized environment in space. High tensile strength carbon fiber 3D printing would also simplify the process of creating carbon fiber structures. And further development of the methods of frontal polymerization would assist in understanding the processes and applications, along with risks and drawbacks. Next slide, please. Finally, we encountered many challenges in our design process, but some of the biggest have to do with resin in manufacturing in space, specifically long-term resin storage in space and pot life, vapor pressure and spontaneous boiling in low-pressure environments of resins and liquids in general, as well as the general complexity of 2-part epoxy systems and manufacturing. And we ameliorated all of these challenges by utilizing our DCPD resin method, which should hopefully counteract some of that. Next slide.
Okay, so getting into our design process, this is an animation. So we started by identifying our key stakeholders and understanding their needs and roles. And then from there, we were able to translate those needs into formal requirements and need statements. After that, we generated multiple concepts and screened them against those requirements. The concept that we ended up going with was manufacturing carbon fiber tubes in a microgravity environment. And once that was chosen, we developed the system architecture, performed trade studies to refine the approach, and then moved on to detailed CAD modeling of the payload and its major components. Next slide, please. And then for our system goals and success criteria, the critical ones, we said that the payload must fit within the Arcus's Boson's locker volume and remained under 400 kilograms and stay within the available power limits of 100 watts peak and 300 watts sustained. And it also has to demonstrate at least 3 operations related to carbon fiber tube manufacturing and microgravity aboard the Arcus's port module in low Earth orbit. On top of that, the system must cure epoxy without external heating, withstanding the thermal effects of the curing reaction, and maintain a 20 millibar pressurized environment for vacuum injection and survive launch loads. These requirements drove pretty much all of our design decisions. Next slide, please. And this slide covers the goals that are important, but not as mission critical. Ideally, the system should be semi-autonomous, requiring no more than 3 manual inputs, which will help reduce ground or crew intervention during the operation. We also want the payload to be able to produce 4 carbon fiber tubes, with each tube meeting specific dimensional and structural targets. And it needs to have the ability to withstand 350 kilonewtons of force, a tensile load. And we finally identified that the target production cost would ideally be around $4,000. Next slide, please. Our system overview, our high-level system overview shows our payload architecture, and the system is divided into 4 subsections. We have our mechanical and structural system, our fluids management system, our communication system, and controls and power subsystem, and the thermal management subsystem. Next slide, please. For our concept of operations, we have this diagram that shows from launch to return. So we begin by launching the payload inside of the bosun's locker aboard the cutter. It'll then rendezvous with the Arcus support module, and a robotic arm will transfer the payload and activate it. And once attached, it will start performing its manufacturing capability and producing carbon fiber tubes in microgravity. And after the manufacturing sequence is complete, the payload will undock from the port module and dock back with the cutter, where it is then returned to Earth and arrive at a designated return site. Throughout this process, communication with ground will be constant. Next slide. And then this is a simplified version of our mission sequence. First, we have our raw materials being loaded onto the bosun's locker, and then the system is launched into low Earth orbit. Then the payload will rendezvous with the core module and be activated. Once it's activated, it'll perform its primary capabilities. And after that, the payload will be deactivated and prepared for return. And the final step is returning to Earth. Next slide, please. This slide will zoom into the internal production logic once the payload is activated. The process starts by checking whether enough material is available, and then initializing the actuators and feeding the carbon fiber. If feeding is unsuccessful, the system attempts an automatic reset before requiring human input. Once the feeding succeeds, the mandrel winding begins and the resin applicator is deployed, and the curing process is initiated. Sensor data is continuously checked to determine whether the process remains within nominal conditions, and if not, then the system will try to automatically adjust the temperature, pressure, or feed parameters. If this correction fails, the ground crew is notified, and the system can either enter an emergency stop or be managed by the ground crew. And if curing completes successfully, then the finished tube will be moved into storage. Next slide, please.
This slide shows the overall system packaging with the Arcus bosun's locker. The locker geometry and CAD were provided directly by Arcus, so our design is fully constrained within this volume. That means all structural components, mechanisms, and all electronics have to fit within this standardized payload envelope. On the right, you can see the engineering drawings with key dimensions, and the left is our integrated CAD model. This serves as our baseline for all subsystem integration moving forward. Next slide, please. Here, we show the initial integration of the carbon fiber spool inside a locker. The exterior panels are hidden in this view, so we can clearly show internal layout. The spool is mounted directly to the side wall of the locker using a very simple support structure. We intentionally chose a design similar to a paper towel holder, so this keeps the mechanism lightweight, easy to assemble, and minimizes the number of moving parts, which improves reliability in a space environment. This also allows for straightforward loading and replacement of material if needed, without requiring complex mechanisms or additional actuators. Next slide, please. This slide focuses on how the carbon fiber is actually processed. So the fiber is wound around the mandrel, which is connected to a motor that provides the rotational motion needed for manufacturing. We're planning to use a cost motor to reduce development risk and simplify the integration. The motor is mounted directly to the floor of the locker using custom bracket, which ensures the proper alignment and structural support during operation. This setup gives a simple and robust mechanism, control rotation mandrel, and enables consistent material deposition while keeping the system mechanically straightforward and reliable. Next slide, please.
All right, howdy y'all. So epoxy is stored adjacent to the mandrel for minimal piping requirements. We selected polycarbonate as a tank material as it is unreactive with the epoxy we've chosen, unlike acrylic would be. Epoxy is ejected from the cylinder using a linear actuator in a syringe-like fashion. This is to remove any chance of gas mixing if you were to use a gas pressurization system. The resin is then transmitted through PTFE tubing, also known as Teflon, as it is also unreactive. Next slide, please. Once the tubes are fully complete, they need to be stored in such a way that they are not free floating around the locker. We decided to use a revolver system for storage. Each tube will be pushed off the mandrel and onto a vacant holding rod, and then will then be rotated out of the way for the next complete tube. This allows the system to produce 5 total tubes, with one staying on the mandrel, which is sufficient to act as a technology demonstrator. Next slide, please. Here are a couple of CAD drawings. On the left is the revolver, and on the right is the mounting bracket for the DCPD tank, along with the linear actuator placement. We can go more into how these dimensions were calculated at the end of the presentation if we have time. Next slide, please. Here's a short animation of just the linear actuator system, how it would act in ejecting a carbon fiber tube from the mandrel. And I think passing it back to Aiden.
All right, so going into a little bit of our preliminary trade studies, there's an animation here, you can just skip through them. But power and thermal requirements means we realistically do not have autoclaves in space, which means we need to look to alternative methods of carbon fiber curing in order to manufacture. So 2 methods shot out to us immediately, pre-preg carbon fiber sheets and 2-part epoxy curing. These are bundled into one of the methods that are available to us. These are using the autoclave and thermal curing methods, and so we deemed them to not be a very feasible way to accomplish our manufacturing goals. Instead, sizing focused on alternate polymerization methods, and these include UV radical polymerization and frontal polymerization. UV radical polymerization utilizes UV bombardment in order to activate polymerization of certain specialized resins, whereas frontal polymerization utilizes a single initiation spot, usually caused by a single spike of thermal energy. And because of the chemical makeup of the resin, this causes a propagating reaction front that is self-propagating and spontaneous without the need for additional thermal energy or curing. On the right here, you can see a research paper showing photoinitiation of a frontal polymerization reaction front, which causes the initially liquid resin to fully polymerize into a structurally sound resin. We ultimately chose frontal polymerization as it allows us to manufacture these carbon fiber composites without the need for expensive thermal systems. Next slide, please. Another very important trade study we did was the method of thermal management. Passive and active technologies are the 2 main methods of thermal management in space, and current space designs are dominated by passive technologies such as radiator cooling and sun shields. There's also active control methods, which are more effective for high heat loads. And if you go to the next slide, we ultimately chose to go for active heat control due to the small size of the payload and the assumptions that the Arcasys port module that the payload is connected to can handle thermal management in some sense. So we decided to manage our heat rejection using thermoelectric cooling, which is solid state, very few moving parts, and relatively inexpensive. So that is what we decided to go with for our thermal management. Next slide. We also did a trade study on heat monitoring. Sensors are a very important part of the system, and making sure that the heat does not exceed requirements is essential so that electronics are not damaged and the curing process occurs properly. There's 3 methods of heat transfer: conduction, convection, and radiation, but in space, the only one that is available to us is radiation. So next slide, please. We ultimately decided to go with, sorry, there's animations here. But we ultimately decided to go with thermal imaging cameras for our heat monitoring, as that allows us to directly monitor the radiation of the system in real time without the need for conduction-based heat sensors. Next slide. You can go past this too.
Okay, so in order to store and use DCPD resin, it needs to exist in a suitable environment. This requires the pressurization of any system interfacing with the DCPD to be at or above its vapor pressure of around 3 millibar. We decided to go with a significantly higher 20 millibar of pressure as a factor of safety. Additionally, we decided to go with a fully inert gas instead of just pressurizing with air to completely reduce the risk of chemical interactions that were not foreseen prior to launch. Some subsystems are listed here. Most important for us is going to be the leakage failsafe system. In the event of a DCBD leak, it needs to remain in its liquid phase so that it may eventually be recaptured by some absorbent cloths surrounding potential leak sites. Next slide, please. There's a bit of animation here if you want to just hit next twice. Due to previous requirements, due to the previous mentioned requirement for handling DCPD leaks, we have decided to pressurize the entire locker rather than using an airlock system. And at first, this may seem kind of sketchy as you're pressurizing effectively a rectangle. But from both hand calcs and some basic conservative FEA, the maximum stress observed in the locker walls was around 36 megapascals, which is far below the yield strength for the aluminum alloy being used. We've also decided to go with argon as our pressuring gas, as is by far the least reactive and doesn't cost that much more over getting a nitrogen. Next slide. So the fluid system has to operate in both microgravity and a rarefied atmosphere of about 20 millibar. And we also need to prioritize minimizing the chance of any leaks in the fluid system. Next slide, please. Hit next once more, please. And so from, wait, I turned around here. Yeah, so using a gas pressurization system will not work alone in microgravity as the gas and epoxy would mix, as I mentioned on a previous slide. So this really only allows for an electrically driven system, as both neither hydraulic nor pneumatically driven pistons provide the precision required for how low our DCBD flow rate is while we're applying it to the tube. Next slide. Hit it next thing, thank you. So the DCBD tank itself pretty much just has to be a cylinder and allow to follow our cost desired part selection. This allows both common O-ring sizing and basic piston head sizing. All right, I'll pass it to James for risk assessment.
All right, for our risk assessment, we used a standard 5x5 likelihood and consequence matrix, likelihood going from very unlikely to very likely, and consequence from negligible to catastrophic mission failure. We identified 4 significant risks, first of which is an ejection jam, which could occur if the tube sticks to the mandrel or is ejected off axis. This was identified as a likely critical risk, but through a linear actuator for dispensing and a Teflon coating, this brings down the risk to a very unlikely moderate risk, which is tolerable for us. Our second risk is an atmosphere leak. We could see that happening as the 20 millibar environment is hard to maintain and is necessary for mission success. This is a possible yet catastrophic risk before mitigation, but through backup argon and a pressure monitoring system, we see this coming down to an unlikely marginal risk that we will accept. Third is a nozzle cure creep, which could happen if the frontal polymerization reaction cures epoxy going back upstream into the nozzle. This is identified as a possible critical risk, but through onboard sensors and a jam clearing mechanism, we have seen this go down to a very unlikely yet still critical risk. Finally, a winding initiation failure could happen if the transfer of carbon fiber from the spool to the mandrel was miscalibrated, causing a system to unspool loose fiber. But due to the jam cleat geometry of the mandrel and active tension monitoring, this is brought down to a very unlikely and critical risk. So we can see that overall, we have created mitigations to mitigate these risks. So next slide, and you can skip past this next one as well. For time, I believe the animations were wonky. One more, please. All right, so overall, we have been able to follow our schedule quite well. We're excited to continue to see what papers we can submit and all that. And next slide, please. I will wrap us up with a summary. We have enjoyed this project. We've demonstrated ISAM capabilities through this. We believe that this is a very feasible project, especially with the commercial off-the-shelf parts. We have a prototype designed, and we have also submitted that report. And with that, we will open it up to any questions if there is time.
Okay, we have about 5 minutes for questions. So first, if there are, well, Brian, if there's any questions in the room, you should just go ahead and have them ask.
No questions from the room.
Okay. Do we have any questions online? So I'll ask a question. But where did you how did you decide to use frontal polymerization and how did you learn about it?
I can take that. Thank you, Dr. Rome. Definitely credit where credit is due. Frontal polymerization is not our discovery. It is the work of some fantastic researchers over at University of Urbana-Champaign, Illinois. They've been doing work on frontal polymerization for several years now, their material science department. And it was their research papers that we were reading that ultimately decided to go with this conceptual design.
Okay. And I was actually at University of Illinois last week and spoke about your project a little bit with Professor Bauer, who's not the material scientist, but he's the engineer. Like there's a question from Harsh in the chat. Would there be a need to stop the chemical reaction once it starts?
I can take this as well, unless someone else wants to jump in. But uh, in our design, the polymerization reaction will be initiated by a thermal shock. So most likely some kind of device akin to a solder, basically a hot piece of metal that we can heat up fairly easily, touching the polymerization at a certain site. And on the mandrel, essentially that front reaction front is going to propagate through the entire length of the carbon fiber tube. Um, we won't need to actually manually stop that reaction because so long as the system is operating properly, that reaction is going to be isolated to the mandrel, and there's no risk of the reaction continuing beyond that. And once it is fully polymerized, it will naturally cool off.
Okay, and then a question from Professor Kinsey. They want you to talk a little bit more about bringing the tubes back to Earth. Could they be used for structures in space?
Yeah. So the current design and the current mission profile that we described here was based off of our approach to this being a research mission. So as a proof of concept, it would involve the ConOps involved going to space, performing the manufacturing purely in space, and then returning for research and analysis. And that is also contributed to the fact that this is a very small scale system. We only have the capability of producing and storing up to 5 fairly small tubes. Um, this is sort of like a lab scale mission profile. And we expect if it is something that is feasible and can be done and works, then it could very easily be expanded into a much higher scale. And those parts could stay in space and be used for in-space construction of structures.
All right, great.
And yeah.
All right, thank you. We're just about out of time. If there's one more quick question, you can ask it. Otherwise, let's thank our speakers again. I don't know if we thanked you the first time. And yeah, we'll have a couple of minutes for the judges to record the score. Then I believe Wormhole is next up, and you can start at the top of the hour.
All right. Thank you all so much.
Hello, everyone. Can you hear us?
Yes, we can hear you.
All right.
And you guys can get started. Good luck.
Hello, everyone. Thank you for being here. We're calling from New Hampshire right now. My name is Savvy. I'm Sarah, and we're studying electrical engineering. We're presenting our project Wormhole, a soft robotic end effector for orbital debris capture. It sits at the intersection of soft robotics, space systems, and autonomous servicing. Over the past year, we've been guided by previous work at the Aerospace Corporation to a somewhat functional prototype, and we'll walk you through what we built, why it matters, and where it's going. Next slide, please. At a high level, the problem we're addressing is orbital debris. Small debris in low Earth orbit is extremely difficult to capture. Traditional systems rely on rigid mechanisms that require precise alignment, and any mistake risks creating even more fragments. Our solution is Wormhole, a soft robotic gripper that uses shape memory alloy or nitinol wire to actuate flexible fingers. The key capability here is gentle adaptive capture. Instead of colliding with debris, the system will conform around it. The fingers will bend and wrap around irregular shapes. Where we are today is we are a functional prototype for validated actuation behavior, and we're continuing to refine the curling geometry, which is the core challenge of the system. Next slide, please. This project was completed by Sabby and I, senior electrical engineering students, and we were advised by Professor Pablo Hume and Professor Kinsey, with mentorship from Jared Fuller at the Aerospace Corporation, who introduced us to shape memory alloy systems and a pioneer behind autodynamic flexible circuits, and additional guidance from Professor Shad Mahmood. Next slide. So here's our program management milestones. Our timeline followed a pretty structured progression from research to prototype. We started in summer 2025 learning about SMA systems and using autodynamic flex circuits as a form of soft robotic at the Aerospace Corporation in El Segundo. By the fall, we established this mentorship and the UNH connection. So we're also doing this for our senior capstone. We have an undergraduate research conference next week, which is super exciting. But in the fall, we focused mainly on literature review, the trade studies, and since this is a pretty new use for the SMA, like the soft robotic application in space, we had to do a lot of literature review, and there wasn't much out there, specifically comparing soft versus rigid systems, and then SMA versus motors. In the winter, we had figured out the components we wanted to order, and we began our prototyping. And in January and February, we were really focused on the finger geometry and understanding nitinol behavior, which ended up being way less predictable than expected. Then it comes to March and April, where we are now. We've integrated sensors, built a full system, and we've assembled our working prototype. Next slide, please. So the impact. Now zooming out, why does this matter? Low Earth orbit, or LEO, is one of the most congested environments we've created. There are over 18,000 tracked objects and many more untracked. To your right, you will see This is a diagram of all the currently tracked objects in LEO with, is it the yellow being debris and the pink being actual in-use objects. So the real issue here is collision risk, because as collisions will create more debris, leading to what's called the Kessler syndrome, where we have a cascading problem. And current solutions for debris collection require very high precision and are difficult to scale. So what we're proposing here is a shift. Instead of precision first systems, we're aiming for compliance and adaptability. A soft robotic capture allows us to interact with debris safely, even when we don't know its full shape or motion. Next slide, please.
Feasibility. Through our project, we validated that shape memory alloy actuation is repeatable under load. We iterated on our finger geometry multiple times to improve curling behavior, and that we confirm that the system operates at low power levels, which is critical for small satellites. We integrated a time of flight sensor to detect objects, and we built and tested a fully integrated prototype that demonstrates feasibility. Next slide.
So the innovation here is shifting from the rigid precision systems to the soft adaptive systems. We have to thank Jerry Fuller and the Aerospace Corporation a lot for their mentorship here, because we like to say we're at the edge of a new frontier here. Basically, for Wormhole, the fingers are compliant, meaning they're naturally adaptable to unknown shapes. And we're able to replace traditional motors with the shape memory alloy. So we're reducing mass and the mechanical complexity. While we rely on passive mechanical behavior, so we don't need extremely complex control systems. Additionally, we have a multi-node design which allows us to control how fingers curl. And finally, we use sensor-triggered actuation. So the system responds automatically to proximity or contact. Overall, we're replacing rigid, high-precision systems with these super lightweight and adaptive ones. Next slide, please.
Wormhole directly connects to high-value missions identified by space and assembly manufacturing. It enables autonomous debris capture in LEO, and it supports robotic manipulation and debris mitigation. It could be deployed for multiple systems to capture multiple targets, and integrates well with future on-orbit recycling and manufacturing systems. So it can be part of a larger ecosystem of in-space servicing. Next slide.
This slide shows the physical design of our end effector. And essentially, we use 3 fingers spaced 120 degrees apart to create a stable, symmetric grasp. Each finger is about 7 inches long and follows a tapered trapezoidal shape, which helps guides objects inward during capture. The fingers are built with a multi-node structure, which allows controlled bending when actuated. And a nitinol wire, as seen with the 2 images on the right, runs along each finger. And when current applied, it contracts and causes the finger to curl inward. Is it possible to click the middle image? It's a video. Yeah. So this is just one example of the, and the video on the right as well, please. 2 examples of real-time actuation. This is a sensor triggered motion. We're using a time of flight sensor, and as an object, that shadow that is caught on camera approaches, we have real-time actuation. This morning, we were actually working on capturing a 5-inch balloon with our 3 fingers. We were hoping to have it ready in time, but it's not camera ready yet. In operation, the system first detects an object for using a time of flight sensor and then triggers the actuation once it reaches a certain threshold, and then the finger will close upon the object. So the key idea here is that we don't rely on perfect alignment, but the fingers are very flexible and they can adapt and conform in real time. Next slide, please. This expands to the full mission sequence. Starting from deployment, the system detects debris, approaches it, and aligns for capture. And then, as said before, a distance threshold triggers SMA actuation. The figures curl and secure the object, and then the system transfers that object to a servicing or recycling platform. So this shows how Wormhole fits into a full orbital servicing pipeline, not just a capture, but an integration into a larger system. Next slide, please.
Required elements. For sensing, we use a time of flight sensor for proximity. For actuation, we use shape memory alloy wires nitinol, driven electrically. Control is handled by an Arduino microcontroller with autonomous triggering logic, and we use a 3-finger design with multi-node and hole geometry. Our integration includes power, mounting, and communication interfaces.
Next slide, please. So there are definitely risks when it comes to Wormhole. The first one that comes to mind is an incomplete capture, and we experienced this morning, actually, while testing. But if an object escapes, the mission fails. So this would require geometry optimization and multi-finger redundancy. So increasing from 3 fingers to perhaps 8. Another risk is SMA overheating or fatigue. So the whole novelty behind this soft robotic actuation is that we have this super low resistance wire. We're heating it by running a current through it, we heat it to a certain temperature, and that causes a contraction. So over time, we're unsure really how long this can last. So we've addressed this with pulse width modulation control and then additional thermal testing. Finally, we have the unpredictable debris geometry. This is where our design helps because the compliance reduces the need for precision. So a lot of our mitigation strategies are actually built directly into our design. Next slide, please. So for trade studies and design decisions, basically we came in with the idea that we wanted to use the SMA soft robotic concept. So it was more comparing the existing options to our alternative option. For actuation trade, while motors have higher precision and they're more reliable, they also have more mass and a much higher power consumption than compared to our SMA. For end effector trade, we chose soft robotics over rigid grippers because it adapts to unknown shapes, and then also it's flexible and not so rigid. So if debris hits it, there's less damage to be expected for the instrument. And then control operations trade, we chose autonomy, as then we don't have to rely on humans, and then a reduction of bandwidth, and it also scales better for operation. Next slide, please.
Communications. The communication requirements for Wormhole are minimal. There's no continuous operator required, only for high-level mission oversight. We used event-based mission communication transmitted during capture. Wormhole has a low data rate required due to the use of the time of flight sensor instead of a camera, which makes the system compatible with small satellite platforms. Next slide, please. Concepts considered. We have explored other designs. We initially considered an 8-finger gripper, but it added complexity and increased our power demand. We looked at vision-based detection, but space introduces challenges, so we ended up going with the time of flight sensor. And we switched to 3 fingers to reduce power demand. And we've known that nitinol and shape memory alloy wires was our main design choice. Next slide, please. Technology gaps. There are still gaps in our technology. Shape memory alloy reliability in space needs long-term validation. Autonomous tracking needs to go beyond simple proximity sensing with the time of flight sensor, and capturing debris is just the first step. We need infrastructure for storage and recycling. Next slide. So there were quite a few challenges. I would say the first challenge comes from us being, I'll say, mechanically challenged, as we're
we focused on electrical engineering for the past 4 years. And so majority of the challenges you'll see are kind of like the interfaces of where electrical systems meet the mechanical systems. So the first challenge was achieving enough of a curl. So as we saw in the video a few slides ago, as we applied a current, the finger curled. And this is the curl pattern, or the curl is a result of the shape form of the actual finger and a pattern of holes, or nodes as we call it, in which we can weave the wire through. So figuring out how to shape the shape form was pretty difficult. And nitinol doesn't contract very much. It's only 3 to 4%. So how can we articulate the geometry in a way to get enough curl to achieve full closure? So we solved this by, we automated a MATLAB script and ran through a bunch of different node spacings and just in-person trial and error. We also had to balance power and performance. There are a few different diameters of the nitinol, but they come with different trade-offs. So if you have a thinner wire, it has a smaller current requirement, therefore smaller power. However, you will not have as much actuation, not as much force. And then vice versa, with an increased diameter, the power requirement goes up, but you achieve a stronger curl. It also does take longer to heat up. So this was a little bit difficult to pick. Early designs were inconsistent, so we also introduced a multi-node structure for repeatability, hence the MATLAB code, and that was definitely the most hands-on and iterative part of the project. Next slide, please. Like a lot of things on this project, our paper is still in progress, but here's our abstract. The key takeaway is that we have demonstrated repeatable actuation and partial capture. We're still working on full enclosure, but we've identified curvature optimization as the main constraint. So this validates the concept and sets up our future work. Next slide, please. So the path to PDR. Looking forward, we outlined a path to the preliminary design review, and this includes refining the geometry further, testing components, integrating systems, and performing environmental testing, specifically vacuum testing for space conditions. Eventually, this leads to platform integration and flight validation. So this is how we move prototype to a space-ready system. Next slide, please.
Summary. To summarize Wormhole, we built a soft robotic end effector using shape memory alloy. We prioritize simplicity, reliability, and low swap speed. It works because it adapts to unknown shapes, and next steps include improving capture reliability and moving toward flight validation. Overall, Wormhole shows that soft robotics is a viable approach for orbital recapture.
All right, next slide. Thank you so much for your time. Any questions?
Okay, we have plenty of time for questions. Like, do you have any in the room, Brian?
Not in the room, thanks.
Okay. Do we have questions online?
Sure. Yeah, this is Jerry. So it'd be interesting to hear a discussion of how you would apply such tiny forces on a debris capture mission. The forces are tiny, right? I think we can all agree with that. What strategy do you use in your system for making use of such small forces?
Hi, Jerry. How are you? That's a great question. I think that we've definitely experienced some tunnel vision on this project. We've been mainly focusing on further proof of concept and getting live actuation and response, I think that would definitely be in the next steps, along with testing, further testing in a vacuum chamber. I hope I answered your question.
So I'll offer one possible strategy, and that is to just recognize that you're going to take a lot more time than a traditional robotic capture using some sort of boom and joint arm. So just expect to take a lot longer to do the job, but that's okay. And you know, take advantage of what you got. The thing weighs a lot less, so it's okay that it takes longer because you've gotten there a lot earlier on the same propulsion.
That's a fair point. Thank you.
There's a question online. How would solar heating from direct sunlight, how the SMA behaves?
Okay, this is a great question, and it's something that we have definitely I've seen, or it's been asked to us before, but since because the whole concept of how the nitinol works here is that there's one of the material properties of nitinol is it's very thermally sensitive, and so we rely on its resistance and, you know, applying a current to achieve a certain heat to contract it. So even within testing here on Earth, for example, what do you call it? Just temperature within a room, we've noticed a little bit of variance as it changes the resistance slightly. So that's something that we would have to also find a way to simulate. I hope that answered your question, but it's a consideration.
It says thanks, so it sounds like it. And Greg, you have a question. Greg, you can go ahead and ask. You're still on mute.
I apologize, double muted. So you talked about how the fingers are adaptable; they can conform in real time. What about the strength of the actuators? And this might be related to Jerry's question about forces, but how heavy or massive a client can these capture based on the analysis that you've done to date?
So we have been experimenting. That's a great question. Thank you. But we have been experimenting with as I said before, there's different diameters of the nitinol, so that will change our power requirements, but like a thicker diameter results in a stronger contraction or stronger force. And so how the force is manipulated totally depends on the choice of wire and the shape form. So I think that would have to be, I can't give you like a solid answer right now, but it would require like further refinement of the actual shape form, the curl pattern. And we have tried to plot a few things on our handy dandy MATLAB of force as it relates to the length of the wire. I can try that one next. Yes, it might be on the next slide. I don't think. I think that the top part shows you how the voltage required goes up. No, no.
Got it. And what I think I'm hearing is that from the perspective of the project, you were a little more capabilities driven. Like what can you do with the nitinol and the shape memory alloys as opposed to requirements driven? We need to capture an object of this size and shape. which makes a ton of sense. And I love the way that you've organized this and the way you presented it. Thank you.
Thank you so much. If it helps, we were trying to make a capture system that would be like deployable on a 27U CubeSat. And then we in lab have been testing with a balloon that's 5 inches in diameter. So it's very lightweight. We can control it. Sometimes we pop it. But we're able to do that currently. Basically just let the balloon fall on top of the instrument. Gravity is the only force. And yeah.
Fantastic. Thank you.
I assume you're popping the balloon because the actuator wire is somewhere approaching 90 degrees C. Is that it?
That is
Or you?
correct, Terry. We're able to hold the balloon for a few seconds, but we've definitely jump scared ourselves a few times in lab. And currently we have an order for more thermally resistant balloons, which are not cheap.
Oh, yeah, the other thing you can do is put a layer of half mil Kapton over the wires as an insulating layer. You're going to need that anyway. Any spacecraft you come in contact with, you're not going to want to put a live current on. So adding one more layer of a very thin, like half mil or 1 mil Kapton film should be something that has minimal or perhaps zero effect on the motion of the arm if you do it the right way, but will prevent those problems and actually increase your performance.
Thank you.
Okay, they were pretty quick, so we have time for another question or two. Otherwise, we'll go on pause while the judges record their scores. Okay, let's thank Team Wormhole again. I think this is our smallest team, right? I mean, I think yesterday we had CSUN. I mean, Jerry, you helped both ends of it, like the team of 20 and the team of 2. But great work, and I'm proud of you guys for taking on the challenge and doing such a good job. So thank you, and we'll be back in 4 minutes with REV-LE.
Thank you so much.
Who probably wouldn't been in the top 2 for best pun of a team name. So, pretty good job there. All right, thanks. We'll be back in a couple. Okay, REV-LE, you guys can probably start warming up, and as soon as we hit half past the hour, go ahead and get started.
Awesome. Thank you, guys. We did have a quick request. We noticed that on the PowerPoint format, slide 30, we had a GIF that was not working. So we were curious if we have our slides here, so we could present, or alternatively, we can move forward with the GIF not there. It just would be a nice visual.
Unfortunately, we are going to be presenting all of the slides and we can't make any updates at this stage.
Okay. Okay, no worries. We will proceed with that. The team is also in the same room and will be on various cameras. So just a heads up.
Okay, let's get started. Good morning, everyone. My name is Miranda Kang, and we're Team REV-LE from Texas A&M University. This is our cosmic final briefing. We're competing in Track 2 of Lunar Operations. In this track, we were tasked with designing a payload that can be delivered to the moon via Astrobotics Griffin lunar lander. This payload must support the development of permanent lunar infrastructure. Moving on to the next slide. Here's just a quick overview of our team. We're a senior aerospace design team. Our advisor is Dr. Maji, and our mentor is Tim Kienberger. Moving on to the mission overview. The motivation for our rover, or REV-LE, which is the regolith excavation vehicle for lunar exploration, comes from one of the largest challenges of exploring and operating on the moon, which is lunar regolith. Regolith is extremely sticky, it's abrasive, it's unstable, and it's very easily prone to erosion. When landers fire their lunar module descent engines, they eject regolith in high-speed dust plumes that can erode nearby hardware and reduce visibility. As of now, there are no CLPS or Artemis missions that include autonomous site preparation, even though NASA identifies landing site preparation as a critical unmet need. REV-LE addresses that gap by surveying, leveling, and compacting the regolith, and research has shown that even moderate compaction can increase regolith strength by up to 2 to 4 times, which would greatly reduce plume kickup and overall build site quality. Moving on to our design process overview, we began with the problem definition stage, where we just identified our primary needs and stakeholders. Next, we moved on to the SCR and the SRR, which fleshed out and finalized our system and subsystem level requirements. From there, we moved on to the SDR and conducted subsystem trade studies that we'll see later in this presentation. We also conducted a risk assessment and preliminary subsystem sizing to make sure that we're still within our mass budget and volume envelope. Our PDR presentation demonstrated our subsystem designs in CAD and also presented our prototype validation criteria and tests before we transitioned into our prototype development stage this semester.
Howdy, my name is Brooke Wolfram, and I'll be talking a little bit about the stakeholders and requirements. Here we identified some of our key stakeholders, namely lunar lander, habitat, and mobility companies. Looking at the requirements on the next slide. This graphic is able to summarize how our 2 main system needs, being able to compact the lunar surface and being deployable on the Griffin lunar lander, were traced through the goals and requirements established during REV-LE's life cycle.
Howdy, my name is David Fumero, and I'll be presenting the system concept and architecture. So this concept of operation shows how the Griffin lander deploys the system and how the system completes its lunar mission. After landing, the Griffin lander will deploy the rover through a ramp onto the lunar surface. The rover will then begin its mission by scanning and surrounding terrain to determine whether the site is suitable for construction or landing operations. Once the suitable area is identified, the rover will move forward and clear the surface obstacles using a front-mounted push plate. This will remove the rocks and debris that could interfere with future operations. Next, the system will transition to ground preparation. A vibration plate that is mounted beneath the rover will start compacting and flattening the regolith to create a dense and level surface. This step is needed to support future infrastructure, landers, or other missions that may happen on the moon. Throughout the process, the rover will communicate data about the terrain back to Earth, and it will also receive instructions from Earth on how to proceed. After verifying the surface is compacted enough to the requirements that we have, the rover will return back to the Griffin lander, where it will recharge and will prepare for the next task. The prototype we built is a JPL open source rover, and its purpose is to demonstrate the mobility and autonomy side. The prototype also accounts for the mass and volume of the compaction mechanism and the push plate to ensure that these can be integrated into the system later on in the future. The compaction and pushing mechanisms are validated using computer simulations. Go to the next slide. This slide shows the system's autonomous decision-making process during surface operations. The system will begin by powering on and sensing the terrain. The rover maps obstacles and evaluates whether the selected area is within operational limits. If not, the mission is aborted or redirected. If the area is valid, the rover will select a path and begin executing passes. As it navigates, the rover continuously senses the environment, looking for obstacles. When one is detected, it determines whether the obstacle can be removed safely. If the object is movable, the rover approaches and clears it using the push plate. If not, the obstacle will be marked and will be avoided. The system then verifies that the removal was successful. If not, they will retry. Once the entire area is clear of obstacles and debris, the rover will deploy the compactor and perform ground passes. After each pass, it will evaluate whether the compaction was sufficient enough and the criteria was met. If not, it will plan new passes until the criteria is met. When the compaction is complete, the rover will restore the results, and then it will check its power level. If the power is sufficient to create another mission, it will do so. If not, it will return to the Griffin lander to recharge. Go to the next slide. This diagram shows the high-level system architecture of REV-LE. At the top, the rover is divided into 6 major subsystems: mobility, communications, power, guidance, navigation and controls, mechanical systems, and command data handling. The mobility system includes the wheels and rover bogie suspension for traversing uneven lunar terrain. Communication is handled through the antenna and transceiver to exchange data from the lander to Earth. With the lander and with Earth. The power system distributes energy from the battery and solar panels through electrical wiring. Guidance, navigation, and control relies on stereo cameras and onboard sensors to enable autonomous movement and decision-making. The mechanical system includes the chassis, push plate, and vibration plate compactor to prepare the terrain. Finally, command and data handling is managed by the onboard computer, which integrates all subsystems. That's it.
All right. Howdy. My name is Ram, and I'll be introducing the system design. So the rover assembly consists of a chassis, suspension system, bulldozer plate, and vibrating plate compactor. And we'll be going into each of these in detail on the following slides. So starting off with the chassis is the rover body that each of the other subsystems can attach their hardware to. It's made of 4130 steel tubing and A36 steel sheet metal that is welded together to form the full assembly. It's able to carry and sustain the operating loads of the suspension, bulldozer, and plate compactor systems while conforming to REV-LE's and the Griffin lander's mass and volume requirements. Next slide, please.
Moving on to our suspension system, our chosen mobility method is the 6-wheel rocker bogie suspension. Some of the defining system requirements that governed our decisions were the mass budget and the volume envelope, as well as our ability to perform in various temperatures and extreme conditions. Moving on to our trade studies, we explored 3 alternative methods, but ultimately selected the rocker bogie due to its performance on uneven terrain, robust design, and extensive flight heritage.
The bulldozer plate is made out of aluminum 775 T6 and is assembled together using fasteners. We've done some static structural and modal FEA simulations to ensure that the push plate can withstand its operational loads without yielding or resonating. Next slide.
Hi, I'm Joshua Cole, and I'll be introducing the plate compactor subsystem. So the primary driving requirement was that the vibration compaction mechanism must generate at least 2.8 kilopascals of dynamic pressure to effectively increase the bulk density of the surface regolith. And to meet this requirement, we designed the plate with the dimensions shown here and selected a motor capable of producing sufficient force when accounting for the plate's surface area and achieving approximately 3 kilopascals, which satisfies the requirement. And the weight of the rover would provide additional static pressure, but would be minimized due to the moon's gravity. We also performed finite element analysis on the plate to verify that the stresses remained below the material's yield strength, and conducted a modal analysis to ensure the plate operates safely under vibration without resonant failure. So overall, this validates that the compactor design meets both the structural and performance requirements. Next slide, please. And this slide is the trade study that we did on the compaction methods. And we compared across different criteria, but the ones that were weighted the highest were complexity and effectiveness, because we needed a solution that was both practical and capable of meeting performance requirements. And from this analysis, the plate compactor scored the highest, but the next strongest contender was the weighted smooth drum roller. But it required additional mass likely to be filled with regolith on the moon, which created challenges with system constraints and integration. Next slide, please. And this slide shows how our plate compactor design integrates with the chassis. So to isolate vibrations from the rest of the rover, we used 4 shocks, which dampen the loads, and then a screw jack mechanism, which allows the plate to move vertically so it can be retracted for mobility and deployed downward for compaction. And overall, this integration design allows us to effectively compact regolith while maintaining mobility and structural integrity. Next slide.
In order to withstand the moon's temperature gradients, thermal protection systems needed to be used. The ones we chose were thermal straps, which will be used to conduct heat away from heat-producing components on the rover, to a radiator panel, which will then radiate that heat away from the body. Along with this, due to its low mass and cost, we elected to choose radiative paint as well for additional thermal protection, just to add on to the effectiveness. Next slide, please.
So for dust mitigation, the main requirement was to prevent the accumulation of regolith on critical subsystems while staying within system mass constraints. And to address this, we selected the electrodynamic dust shield, which we did a trade study on, which uses electric fields to actively remove dust from surfaces. And this solution is effective while remaining lightweight and low power, with each unit having a mass of about 0.2 kilograms or requiring only 2 to 4 watts. Overall, this approach meets both our performance and system level requirements. Next slide, please.
Hi, I'm Wayne Williams, and I'll be talking about the communications and electronics. The design of our communications architecture was driven by 2 requirements, the first being a range of signal strength and the second being a range for the rate of data transmission. This ensures that REV-LE can maintain a reliable link with the Griffin lander throughout surface operations. After a trade study that explored different options, we selected this UHF transceiver paired with an omnidirectional UHF antenna. We chose this architecture because it offers strong spacecraft heritage with a high TRL, it has very good receiver sensitivity, it has low received draw power, and an omnidirectional gain. Overall, this gives us a communication solution that is well suited for REV-LE. Next slide, please. For the electrical power subsystem, this design is primarily based on requirements regarding the range of power output and a range of energy. This design is centered around a lithium-ion battery pack, which weighs in at an estimated weight of 15 to 20 kilograms. The battery is sized at 48 volts and 52 amp hours, which gives us about 2.5 kilowatt hours of usable energy. This is enough to support one full worst-case site preparation cycle and aligns with our requirements. To recharge and supplement the onboard power, we selected these gallium arsenide solar panels. At about 30% efficiency, we would estimate that roughly 1.77 square meters of the panel would provide around 700 watts, and this combination gives REV-LE both the energy storage and generation capability needed for demanding lunar operations. Next slide, please.
Howdy, everybody. My name is Evan McQuaig. I will be presenting REV-LE's component selection for compute and autonomy. First order of business for the team was to select a flight computer with high capability for the autonomy needs required for our flight envelope. We selected the AITech SP1, of which we will be using 2 redundant flight computers. The AITech SP1 was designed specifically for deep space autonomy with capability to inference things like AI models and run perception stacks necessary for relative navigation. We will couple this with non-volatile storage, also from AITech, called the S993. This can get up to 1 terabyte of non-volatile storage. Combined, these compute power and memory is sufficiently adequate to run autonomy systems similar on Earth. Moving to the next slide. Here we have the sensor suite selected, in which we decided to utilize a IMU, stereo cameras, and time of flight computed from the lander utilizing our communication. For the IMU, we went with the Northrop Grumman LN200S, and for the camera, a 2 3D plus 4 megapixel RGBs. These both have flight heritage and are well within mass and power limits. On the software side, we noted the availability of open source methods such as RPNG's MINS. MINS is a modular EKF, so of note, not only can we do our visual inertial SLAM with built-in time of flight from the lander, this is also modular to be able to build up once the infrastructure on the moon expands to include things like GNSS. Moving on to the next slide. Here we show the trade study of exactly how we came to our final decision to use the FOG IMU, Viz cameras, and time of flight with lander. We also considered different architectures, mixing things such as star trackers, wheel encoders, and LiDAR. Of note, the final decision was made to go with the architecture that we utilize, mainly because we met major reliability and accuracy metrics while also being able to provide high mass efficiency due to the fact that these systems are also utilized in other parts of the rover. Moving on to the next slide. Here we have path planning. So now that we've developed a relative pose and point cloud using SLAM, we can utilize open source software packages such as Isaac, ROS, NVBlocks to develop a mesh in 3D space and a cost map. So this will enable the rover to only choose safe solutions. These safe solutions and the parameters feeding into the cost map are going to feed out of a simulation in a physics environment from a package such as Project Chrono. Now that we've developed a cost map and we have feasible methods, we now want deterministic timing in a way that we can optimize our route. For this, we have open source methods such as OMPL's BIT star. Moving on to the next slide.
And now we'll be talking about our proof of concept prototype. Next slide. For our prototype, we used the NASA JPL open source rover platform to validate the suspension and mobility approach behind REV-LE. While this prototype does not include every subsystem from the final design, it was useful for testing whether our mobility concept works in practice. It uses a similar 6-wheel, 6-motor rocker bogie suspension architecture, which is the key feature that we wanted to demonstrate. The prototype is built entirely from commercial off-the-shelf components, which makes it practical to assemble and test within the scope of our capstone. Most importantly, it allowed us to evaluate how a rover with this kind of suspension handles uneven terrain and maintains stability while driving through sand or other obstacles that it could meet on the lunar environment. Next slide, please. So this slide shows one of our main mobility validation tests. In the gradability and obstacle negotiation test, the prototype successfully traversed an obstacle which is 20 centimeters high, while also handling terrain with a grade of more than 20 degrees. This directly supports two of our mobility requirements. This test results show that the rocker bogey configuration is capable of distributing load effectively and maintaining mobility across challenging terrain. Next slide, please. And our final prototype validation focused on rollover resistance and overall static stability. In the side tip test, the rover passed both lateral and longitudinal slope tilt testing, which met the requirement and avoided tipping on slopes up to 35 degrees in either direction. The rocker bogey suspension helps by keeping the rover's wheels engaged with the ground and distributing the chassis motion more gradually as the terrain changes. So overall, these tests gave us confidence that the suspension concept of our design can meet the demands of the mission environment. Next slide.
So to validate the compactor design, we developed a simulation in MATLAB Simulink to evaluate the feasibility of vibratory plate compaction. And so the model incorporates the motor characteristics, damper properties, and plate parameters, along with a soil model represented as a linear elastic system with properties chosen to approximate loose sand. And the equation shown captures the stiffness and damping behavior of the soil reaction force as the plate penetrates and oscillates into it. And from the simulation results, the system generates approximately 4 kilopascals of dynamic pressure and about 7 kilopascals of static pressure, meaning that both of our static and dynamic pressure requirements are satisfied. And a visualization of the plate oscillation is shown on the bottom right. Next slide, please.
To validate our perception and autonomy stack within a time-constrained environment, we decided to focus our scope on demoing the compute-heavy perception on flight-analogous hardware. So for that hardware, we selected a Z Mini camera running on a Jetson or a Nano Super Development Kit. We plugged this into the software that was available to us open source, being NVIDIA's CUV-SLAM and NVIDIA's NVBlocks. On the right side here, you can see a demonstration of our perception and autonomy working. In the middle right is the raw data feeding out from the camera. Of note, the data selection environment was a variable lighting condition environment in which we have a dark environment, we have shadows, and we have stray lighting. So really demonstrating our ability to develop a feasible cost map within a variable lighting condition similar to the moon. Next slide.
Moving on to our risk assessment slide. For the sake of time, I'll just be covering one of these risks from each of our categories and the mitigation strategies that we chose. For dust contamination, we opted to apply dust-sealed joints and electrostatic shielding. For the risk of compaction tool failure or jamming, we chose fatigue simulations and a quick disengage mechanism. Finally, for the risk of electronic overcooling during lunar night, we implemented our thermal straps and TMS system, as well as thermocouples that monitor the temp drops so that we stay within our operating temperature envelope.
In order to do our cost estimate, we used an analogy-based approach using similar rover missions, those being Curiosity and Viper. Costs were compared and scaled based on system complexity, mass, and scope to provide the breakdown shown here. Development and launch cost is estimated to be at $1.27 billion, which is reasonable to be able to fund within the allotted 5 years, and a yearly operational cost of $62 million. Looking forward to our next steps on the next slide. We plan to focus on autonomy validation by developing and testing our path planning and control algorithms by simulating potential lunar conditions and running Monte Carlo simulations in Isaacson. From there, we will validate full system integration with fully developed hardware elements, including the compaction mechanism, bulldozer plate, and thermal protection systems. Next slide.
Finally, throughout this entire design cycle, we learned a lot from it and have a couple lessons learned. For starters, during the inception of the project, we had to think of many innovative ideas. The one we went with was the electric vibration plate compactor for the lunar regolith. But some other ideas we considered initially were a 3D printed regolith-based concrete device, and also modular self-servicing construction and clearance rover. These bottom two options were not chosen mainly due to complexity or time constraints. Another things we thought about were some technologies that would need to be developed to help further refine REV-LE. These include more advanced autonomous planning algorithms, some more characterization on vibratory plate compaction, especially with regolith, and finally, some more advancements in low gravity dust mitigation technology. And finally, there's a lot of challenges that needed to be overcome during this entire design process. The initial stages, some challenges we went through were the fact that there's not much liquid water on the moon, if any, right? And liquid water is normally used for compaction on Earth. So we've had to think of ways to go around that. Another issue is the mass budget, limiting the compaction ability of the rover. Most compaction devices on Earth are quite heavy, so this 200-pound mass budget was a challenge we had to work around. And finally, during the actual prototype building stage, we had to do a lot of troubleshooting for hardware and software on the PCBs. So we definitely learned a lot there. Next slide. And finally, as engineers, we see this as the groundwork, like quite literally, for the next stages of space exploration. Our team is very proud of how far this design has come, and we want to thank you for your time and attention, and we'll be very happy to answer any questions now.
Okay, do you have any questions? Put in the chat or raise your hand or come off mute.
Hey, this is Crispy over at KSC. Wow, it's been a day. Am I coming in okay?
Yes.
All right, wonderful. First off, I have a bunch of questions and such, so if you want to follow up afterwards, I'm happy to do that. Maji has my contact info. You can just say that Crispy from UF has a bunch of questions for you. But just a couple of quick things right off the bat. Very good presentation. I very much liked how you called out each individual requirement and derivative requirement as a means to show your design. But as a question to you, because you have all those requirements, how many of those were self-imposed out of curiosity? Because there were a lot of those that seemed outside the prompt. So how many of those did you actually derive yourself? And how much do you feel that those self-imposed your design?
Well, in the case of the cosmic requirements, it was basically only the mass and volume envelope, and everything else, like the TMS requirements, those system level requirements, those were from like the lunar environment. And then we had a bunch that were, what's the word, performance based. We wanted to have a suitable range of operation that would be good for good for our mission goals and our requirements. So a good amount of our requirements were self-imposed, either because of our advisor input or because of our own self-imposed subsystem leads, just picking what they wanted for each of their subsystems.
And the reason I ask and the reason I'm pointing this out is while I love requirements, don't let those self-constrain you too much. As you are pushing the boundaries in the design, it's good to understand which ones you have flexibility with. So for example, you had a requirement in terms of data rates that was kind of a narrow band. I would claim that I would be questioning where you found that from. And if you could push that, then understand where you can push those bounds. Because technically requirements mean it's a go or no go. So just trying to make sure that you don't constrain yourself too much because you self-imposed that sort of headache onto yourself. But still, I liked all the requirements. I'll do two more things, but if I have time, I'll be able to ask any other ones. You chose stereo cameras. Why stereo instead of a mono camera system?
Sure. Yeah. So I guess the decision to utilize stereo cameras as opposed to the mono camera system is the ability to identify in 3D space and run SLAM independent of all other sensing. So a big emphasis was put on redundancy within this rover, and a mono system is fundamentally limited to struggling within a 3D environment to construct a 3D point cloud, definitely is possible utilizing motion. But in order to create a static 3D point cloud, we wanted the ability to perform that. So that's why the decision was made to go with stereo as opposed to mono. Additionally, on the risk side, you kind of deal with a bit of hardware complexity, but you also get a bit of redundancy with that. To your point, it is definitely possible using motion to construct that point cloud using mono. But the ability to go from stereo to mono is much more sufficient than a kind of zero fault tolerant one system where we're just using one camera.
Thank you. Yeah, and the advantages and disadvantages are always good in that. Depending on the amount of how close you want to get, maybe a mono camera might be good if you're just saying, hey, I want to understand the terrain from X distance. Stereo really gets you that fine precision, but it also adds the complexity of the system. The last thing I'll ask, and then I'll toss it over to anyone else here, is you showcased a prototype where you had actually I want to ask this one. I'll ask this one instead. Your costs, you had them in terms of billion and that sort of aspect of things, right? If I told you you only had 5 million, how would you scope this project? I know that's a curve.
I can take that question. Well, we would definitely try to adjust our costs. So we used an analogous cost model. This was just something that we wanted to get a ballpark in. For the actual flight vehicle, we would just have to adjust our cost allowances for each of our subsystems. So we would probably keep our software and have to adjust the actual the compaction ability maybe, or some of the other aspects of the rover. But what's most important, I think, is reaching our desired area of compaction and really validating and characterizing that design so that it's usable and implementable with certain information, like especially with Artemis 2's information. One of their big deliverables was having or getting locations of sites that could potentially be a great landing site. And we want to be able to characterize this rover so that it could use information like that as we move into like the Artemis space age, and really be able to successfully compact and then verify the safety of that for our astronauts and our landers.
Okay, great answer. The thing that I was really getting at there is, as soon as someone gives you a cost aspect, you should understand where your priorities are. And even if it's a, hey, I need to get rid of the rover aspect, you understand where your true novelty and where your true dedication is. So in this sort of case, you highlighted the software and aspect, and even if you got rid of the chassis, you at least know where you want to go. So those are my questions. Kick me off.
Okay, yeah, we kind of let you run long, Chris, because we're at the end of the session. But are there any other questions? Okay, hopefully the judges have recorded the scores. Yeah, you know, if you want to continue the conversation, that's fine. But we're gonna go and break, I think, until 2 Eastern. Yeah, there we go, 11 Pacific. So enjoy. Hopefully, I'll see you back in an hour. Hope everyone down in Kennedy had a good tours this morning, and I'm looking forward to seeing your briefings after lunch. Thanks all. Okay, all, we're back. If like I think the next team is in the room. Who is it? Oh, yes, the Orbital Gators. And Brian, if you want to handle the questions since they're in the room, I think that would be helpful. Just a note is the second talk, Moonwalkers has withdrawn, so we'll just go silent for those 30 minutes, or we can have discussions, and then University of South Florida's at 3 p.m. But yeah, Orbital Gators, once that clock ticks over to 2 o'clock, you can get started.
Mic check in the room. Can everyone hear us?
Yes.
Okay. Now I'm on. Sorry, I think I took your seat.
Don't worry about it. It's okay.
Everybody sitting here too?
No, it's not my fault. It's weird because it was buzzing.
Oh, I think it's.
Yeah. Is it a government phone?
Are we allowed to have our phones off?
Even better.
I'm just gonna leave it.
I know I'm section.
Yeah, put her on too.
Let me sit over here.
Yeah. Andrew.
Yeah.
You should sit. Yeah. Sit at wherever else.
For how?
Nice to look.
Yeah.
The video's not that high quality, so they can't tell.
We also close it.
Okay.
All right, now it is. Well, don't close.
You can also.
Very fancy.
No, all I have is no ABC or I do not want to see. I'm not hearing. I'm going to go to the set.
Is it almost done?
Yeah, he should be.
Doesn't he have the phone?
Oh, there he is. He can sit up there. He's not going to be able to be seen. No, we moved the chair back.
Oh,
He'll be
okay.
seen. I just slide those on my phone if anyone needs to reference. Yeah, do you? No, Andrew's good. All right. Is everyone here? 1, 2, 3, 4, 5, 6, 7. All right. Are we good to start? Can you guys hear us?
Yes, we can hear you.
Wonderful. So we are the Orbital Gators design team at the University of Florida, and this is our final briefing. So we are developing a toolkit that will scan the lunar surface called Aurora, which is advanced underground resource observation. If you could, the next slide. So this is a little bit about our team. I'm the project manager. My name is Andrew Dischuk.
Chief Engineer Max.
I'm the computing lead. My name is Om Prabhatia.
I'm the principal investigator, Aiden.
I'm the systems lead, Grayson.
I'm the design lead, Paige.
Manufacturing lead, Brady. And then Bryce wasn't able to make it today, but he's our drill system lead. We also want to say thank you to Brian Zetlin, Kevin DiMarzio, and then we want to say thank you to Professor Generale and Dr. Crispy, who aren't here right now, but they are with us. And if you go on to the next slide. This is a little bit of our program overview and the structure that we use for our design team. So I'm the program manager. I oversee both the PI and the chief engineer who give inputs to the system lead, and they oversee the subsystems of our team. And then on to the next slide, please. And our mission is going to be mapping the water and helium-3 across the lunar surface using our system toolkit. We're able to see where water and helium-3 are. And we want to generate a reserve model, which we can go on about a little bit later, that will guide future in-space resource utilization on the moon. And then we can move on to the next slide. And then if you could press the next button for me, please.
All right, so Aurora aims to characterize the location of helium-3 and subsurface water ice. Why are we doing this? Well, we actually need a map of resources before we go to actually find them and then process them. So that's what we're doing with this. If you could hit the next button. So we need to know how much it is and where it is, and that will guide future missions.
All right. And then if you could press the next button for us, please. Thank you.
So water ice is critical for a lot of different things on the moon. First of all, there's propellant, which you can make out of it, and then there's also life support systems. And helium-3 is a little bit of a different story. It's something that can be used for fusion in the future and also for medical things. So it's more of like an economic value. And like I mentioned before, these things are important for missions such as Artemis, but also other missions. So for like commercial companies like Interlin that are interested in mining helium-3, they would need a map beforehand. Next slide, please. And a little bit of background, if you could hit next a couple times. All right. So what we're going to do is we're going to take a look at the surface dielectric contrast or spectral imaging, and then we're also going to look at the concentration of helium-3 via some other methods. Particularly for the helium-3, we're going to focus on ilmenite because it captures 10 to 100 times more helium-3 from the solar wind than other lunar minerals in the regolith. Next slide, please.
Now we're going to go over our agenda for the meeting today. We're going to cover the conceptual design. So it sort of covers a little bit of what Aiden mentioned with our project impact, whether it's feasible or not, and the innovation of our design. Then the program overview, which deals with how we will be interfacing on the moon and how we'll operate on the moon as well. Next will be the systems operation, and then that will give us more information as well. Okay, and then I'll finish off the slide. Lessons learned, those will be the critical things we learned, and then finally the prototype. All right, and then next slide, please. Conceptual design portion, like I mentioned before, is going to be our philosophy, the impact that we have on the moon and future missions, as well as the feasibility, site selection, and high value missions that we advance.
Next. Hit next slide 3 times. Okay, so put simply, the guiding philosophy is to build a modular, reusable platform that is resilient to the lunar elements and is also capable of measuring resources on the moon over a large area. Next. Oh, got it. I didn't even know. I don't think you can hear. All right, project impact. Basically, our goal is to reduce the risk of blind lunar mining to justify multi-billion-dollar investments in the future for drilling missions once we know the abundance of the economic catalysts being water and helium-3. This also gives us a foundation for in situ resource utilization for future missions where they can live off the land because they have more data based on water abundance and helium-3 abundance. And this also directly supports NASA's mission to build sustainable locations on the moon where resources are dense and permanent infrastructure can be effectively built. Next.
And then we're going to talk about the project impact and the different areas that we see its effect. So we're going to see industry, academia, government, and then the different parts of the impact. So in the industry, we'll see helium-3 with companies like Interlun, where you see that arrow pointing from Interlun, the purple square into the helium. And then helium, like Aiden mentioned, is a large commodity for the future. And for academia and industry, we have sensing correlation development. So we're primarily using correlations between our sensors to determine the quantity of helium-3, not necessarily where it is. And then that will help industry leaders like Interlun and then academia learn more about the lunar surface and geology in general. Government for NASA, we'll have with lunar mining, there is going to be lots of extra materials. So we'll have lots of ISRU materials that will be available and also water for future missions as well. And then next slide.
So a little bit about the feasibility of this. Helium-3 is mostly concentrated in areas where you've got high weight percent helium or high weight percent ilmenite on the surface of the moon. If you take a look over at figure 4 on the right, we've got in red the areas with the higher concentration of helium or ilmenite, which correlates with helium-3, particularly in the mare. It also correlates with a long surface residence time and fine grain regolith size. Looking a little bit at the scoping, like I mentioned before, the mare in particular, the highest concentration regions are in the equatorial area,
particularly Mare Tranquillitatis, which is known for Apollo 11, and Oceanus Procularum. And these were previously measured via UV, vis, and NIR spectroscopy. So it's also important to consider not just what's going on the surface, but what's happening at depth, which is what I'm looking at in figure 5 here. Figure 5 shows Apollo core samples helium-3 concentrations at depth. And you'll notice that there's not really like a smooth line. And what you're basically seeing there is the amount of helium-3 is controlled by just impact events. So it's kind of random. It's not really a function of anything. Like I mentioned, helium-3 is implanted by solar wind, so it matters how long it was on the surface, which is why there's no constant stratigraphic distribution. And there's also the grain size for the layer of regolith that affects that as well. We're going to indirectly measure the amount of helium-3 by a nanophase iron, which can be measured by a magnetometer. Next slide. And feasibility for water. So water is a little bit of a different story. Water is mostly concentrated at the lunar poles, but that doesn't mean it's not in other parts of the moon as well. If you take a look at the figure below, that shows suspected water concentration from a study. There is a little bit of ambiguity because OH and H2O do overlap in the 3 micrometer band, but there is some idea that there might be water in some of the mid-latitudes. We're going to make sure of that via GPR, so ground penetrating radar scans for dielectric contrast for the water. So we'll be looking for subsurface ice as well as stuff closer to the surface. And the subsurface stuff should be able to stay present due to thermal stability at depth. And this should allow us to build refueling hubs if those resources are there. Next slide. Our actual design for the rover. So first off, we're using a standard rover platform from Astrobotics Polaris rover. In particular, we're doing this to save time and cost on the design. So we're more interested in the actual instrumentation rather than the mobility part. So we decided to save time and cost on design and testing via that method. We're also using a lot of heritage methods for sensing. So UV, vis, and IR, I mentioned those earlier. We'll also be using those. Ground penetrating radar has a lot of heritage use on Mars as well as the moon, and magnetometry has been used in a lot of different things. And our system that we're really innovating on is the drilling system. So we'll be doing an auger that bores a hole in the ground that will then lower a magnetometer in to measure that nanophase iron. Next slide, please. Next.
So within the next 5 years, because we have those heritage methods, we have an integration path to a final product that is fairly approachable. And then next we have a direct measurement method using the GPR and using the method that we created, the auger drill probe, which will be used as well. So we definitely can get this funded and complete it within 5 years.
All right, advancing high-value missions. So Aurora will pave the way for lunar industrialization by reducing the risk of commercial mining, by providing a prospector's map for future rovers with extraction hardware. It'll also establish the moon as a refueling hub by characterizing the water reserves along with helium-3. That way, lunar drive propellants can be easily made on the moon later on. Also, it'll advance fusion on Earth by giving us a roadmap for clean energy through the data provided by our mission with Aurora. Also standardizing technology with a modular tool chain of spectroscopy, drilling, and thermal analysis that can be integrated into future rovers. Next.
So now we're going to go more into our ConOps. So what we see here at the first step is going to be our Aurora surveying tool. So that is the prototype that we developed, and that is going to be what is going to be sent onto the surface. It's going to go onto the surface, it's going to survey, and then in the second step, what we see is helium-3 sampling with the lunar penetrating radar or the GPR and spectrometry. The next thing will be the direct sampling using the Aurora drill probe or the ADP, and that will be scanned using mass spectrometry with the quadrupole mass spectrometer. downlinked to Earth, and then with that, we develop a map. And next slide. Okay, the instruments. So starting off, alpha particle X-ray spectrometer, elemental abundances such as titanium dioxide, which is an indicator of ilmenite or a proxy for it. Multispectral imager identifies mineral absorption wavelengths. Ground penetrating radar, or sorry, magnetometer first. But by drilling, this can be used to map out images of mineral absorption wavelengths. And then, yes, solar wind implantation, actually. And then GPR, primary tool for water ice detection by using electromagnetic pulses. Electrostatic analyzer, basically measuring the wind flux from the sun. Quadrupole mass spectrometer, that'll sort the ionized gas molecules. And then with higher precision than a regular mass spectrometer. Automated grain size analyzer, that'll identify higher surface area to volume ratio, so where the helium-3 is implanted more. And then basically using the drilling probe plus the mass spec coupled together can give us direct ideas of where the helium-3 actually is and verify our proxy data. Next. All right, and then I'll go over our system requirement structure that we used in presenting our SRR. So the first high level system is the mission statement. So that will define our entire mission and what we're planning on doing. Then below that, we have our mission objectives. So the key things that we want to find and prove within our mission, brought down to the success criteria, which are going to be the things that we prove, the things that we do to prove that we've reached our objectives. And then our more binary requirements, like our system requirements, which break down into either subsystem requirements or tool requirements. So like the Aurora drill probe that Max mentioned, or the ground penetrating radar that you mentioned, and into different subsystem requirements, sort of like our team that works on making the rover sustainable on the surface, so being able to last longer. So that would be like our thermal teams, our regolith prevention teams, our teams such as our power teams, anything that takes care of the rover and future missions. And next slide, please.
So I'm just going to talk a little bit about our systems overview and how that fits into the guidelines given by Cosmic. To start off, our mass and volume were both well within the guidelines given. The rover weighs about 14 kilograms, which is much less than a 200 kilogram allowance, and takes up about 4,800 cubic centimeters of space, well within the 3/4 of the Griffin space allocation. Additionally, as put on some of Max's slides, the power for all of our tools that we chose is well within the 80 kilowatt allowance. Our bus is completely compatible with both the Polaris rover, which we're going to assume interface with, and the Griffin lander, which I'll talk about a little more on the next slide. Additionally, our launch and descent environment, our design reflects thermal and mechanical things to be expected during launch. And our capability demonstration, which we showed last week when we went to the Marshall Space Flight Center and we got
Did we just lose?
I think we just lost the room.
Oh.
Oh, are you guys back?
Yeah, oh, we're Yeah. back. We're back. All right.
Okay, good.
Did you get all of that?
Like you just started talking about going to Marshall.
Okay. So I was just talking about our capability demonstration and showing how like our project is actually feasible. We got to test out our drill prototype at the Marshall Space Flight Center last week, which was really cool. And then also we completed analysis on our mass, volume, power, and dust tolerance. Next slide. And then as I was saying earlier, we're assuming that the Aurora rover, it can interface with any standard LTV platform, specifically the Polaris, and can also interface with the Griffin lunar lander, especially with the Griffin for, we're going to assume power from the Griffin, so inductive charging from the solar panels on there. And then we're also going to assume use of primary comms, power hub, and centralized PNT from the Griffin lunar lander. Next slide. And then this is just showing again that the Aurora can interface with the Griffin as well as with the Polaris rover. Next slide. And then these were some of the innovative ideas we came up with when we were working on the project. The second two, the integrated regolith maturity package and the descent deployed penetrating spike array, were initial ideas in the beginning for how we were going to scan for helium-3. However, we decided to disregard those later in the selection process. We wound up going with a bowl cut dome design, which basically works. The dome sits on top of the regolith and it heats up the regolith and it like puts out volatiles, including helium-3, and then you can monitor for changes in atmospheric pressure. However, due to some cost concerns with that, we later refined to have the drill idea, which Aiden was talking about earlier, which we actually did have on our prototype. Next slide.
All right. So we came down to some 3 technologies that we thought would be the most important to develop for our mission. The first, of course, is the Aurora drill plunge. That's going to allow us to actually stratigraphically measure the nanophase iron, which indirectly determines the amount of helium-3 by telling us how long the different layers of regolith were actually on the surface and being implanted with solar wind. Also, the ground penetrating radar, which allows us to vertically measure the regolith grain size to indicate the density of helium-3 possibly in the regolith, as well as the possible existence of water ice, and then the UV, vis, and NIR spectroscopy that we use in situ to measure surface titanium dioxide to make sure we are in higher concentration TiO2 areas in the local regions that we visit. Next slide.
Now, for some of our design challenges. At first, it was difficult to determine a helium-3 detection method that worked well for our mission. And there's many different methods like scanning lunar surface regolith or taking samples. And so we actually ended up for our final system choosing both. We went with both sampling and scanning for extra certainty. It's also difficult to choose onboard sensors. There's a lot of sensors available that can measure helium-3 correlations. And some of them are infeasible or have too high power requirements or charge cost. And so we needed to include a suite that fully suited our needs. And for scope creep, our preliminary designs featured a lot of components and features that were too complex or out of scope and really drove us off path. Next slide. And so here's just some of those design challenges visualized. And for our helium-3 detection methods, like I said, we ended up doing both. For our scope creep, we narrowed down the scope to, instead of building the rover as well, we made the rover a payload. We made a system of payload rather than including the rover system itself. And for onboard sensor selection, we did ample research on every instrument possible and chose a selection of those that meted our needs. Next slide.
Now we'll go over our prototype a little bit. And if we can move on to the next slide, just so we can move a little bit faster. So here's going to be the scope of our prototype. Like we said before, we have the auger for drilling, which plunges into the surface, a Jetson or Nano used for developing the map, the bus housing for tools, and internal components communication using the Jetson as well. And next slide, please.
So as far as utility, how this prototype advances the mission, well, it provides a proof of concept for the structural constraints using the physical bus housing and the chassis. Given the P&T algorithm to give live position, navigation, and timing tagging to every single data point using the onboard software and the onboard computing, interfacing between the onboard sensors we've proven that proof of concept, as well as controlling the drill using the onboard data logging software, while also being able to output and downlink signals using the RF transceiver on board. Next slide, please. So what was demonstrated during our testing at the lunar testbed at the Marshall Space Flight Center, we were able to successfully traverse through the lunar regolith testbed, and our rover was structurally sound. As far as drilling goes, as you can see in the photo, or as you can see in the figure on the slide, the auger was working. It was drilling into the lunar regolith. However, further tests need to be done to further ensure that the auger is mechanically functioning. The regolith grain size was not representative of that of lunar conditions. The computing was validated, and the suite of sensors were just the magnetometer and the thermal camera. We did not have the full sensor suite, which Max had described earlier, due to prototyping constraints. And that is what needs to be tested further. Next slide, please. Here you can see the system architecture for the data handling and communication system. We have our onboard processor is an NVIDIA Jetson Aura Nano, and those go to our onboard sensor suites using the 40-pin header. Also on board is an RF transceiver, and connected to that is the motor drivers and the power bus. Next slide, please.
And for our system TRL, just some quick landmarks. At TRL 1, we established we wanted to do lunar resource mapping. TRL 2, we came up with the ride-along rover payload concept with the auger and magnetometer. TRL 3, we validated the auger and magnetometer independently. And then TRL 4 and 5 is the integration of those mechanical systems and electronics into the bus payload and testing at MSFC. Next slide.
Okay, guys, yeah, you really have to wrap it up. Just
Yeah. All right. If we can go to the last slide real quick, and then we'll finish up there. So here we are, as Aurora, we're trying to build a foundation for the future lunar economy, sort of building for the companies like Interloon, NASA, and future Artemis missions. And we currently have a concept of modular reusable sensor payloads. We have functioning TRL level 3 to 4 prototypes, and we're trying to build trying to support the development of a proven reserve model. And then our target launch is about 2031 aboard the Astrobotic Griffin lunar lander. And then questions.
okay. Any questions? Okay, do we have any questions online?
I think there's a question, but they need to speak up. Is it open mic?
Yeah. No questions.
Okay, yeah. So the question I was going to have is I alluded to it earlier, but you know, there's the NASA ignition, and there's basically an open call for, hey, do you have idea for payloads for sending to the moon? So I was just curious if you guys are going to respond to that or pursue that.
Yeah, so that's something that's been not stressing all of us out, but something we've been working towards every day, and that's what we're working towards.
They've got their advisors on the hook for that.
Yeah.
There you go.
That's why they're here with us.
Okay. If there's no more questions, we'll have 2 minutes for the judges to record the scores. Unfortunately, like the next team has withdrawn, so we'll have a 30-minute gap, and then we'll be back at I guess 3 o'clock Eastern. Yeah, noon Pacific.
Thank you, guys.
Right. Thank you so much.
That was good. That was better than
I know. I didn't get to preview.
Okay, as soon as we hit top of the hour, you guys can start.
Hey, Jacob, can you hear us?
We can hear you.
Okay, all right, whenever you guys are ready.
Okay, all right, welcome in everybody. We're AIAA from the University of South Florida, and here we're to demonstrate our telescoping robotic arm module, or TRAM for short. Next slide. And yeah, here is our team overview. I'm Ethan, and yeah, we got a good team of 6 engineering undergraduates here. Next slide.
Okay, so the executive summary. So as we know, space has become a sort of expanding market for different kinds of technologies, and to kind of understand like what is out there, how can we expand our infrastructure, our reach in different parts of space, such as like a lunar environment, a Martian environment. And so this kind of also just expands our curiosity. And so because of that, we need more technological advancements. And so one way we're doing this, or a company is doing this, is Arxis. And so their mission is to help reduce the cost and the complexities of space missions, and by delivering multiple payloads within a small satellite using the port module. And if you go on to the next slide. Okay. And so the Arxis, the Bose's locker gives us several constraints and limitations, such as constraint for volume, mass constraint of 400 kilograms, available power of 1,000 watts, and then a sustained power of or constant power usage of 300 watts. But we believe that our prototype, or our TRAM, is not affected by these, or is not limited or inhibited by these constraints, as we have considered all aspects and how we can use the space and resources provided by the locker to kind of make an effective technology that goes with our track. So the locker is also a sensor-equipped enclosure, and it's mainly used for payloads that are protected from the harsh environments of space, such as micrometeorites, radiation, and things of that sort. That's it. Next slide.
Okay, so with the intent of TRAM, it is able to bolt, it is able to screw, it is able to do many manufacturing capabilities. And this is very important, as right now a lot of satellites are launched as single use, and they either burn up in the coming back to Earth, or they contribute to space junk. So what we intend to do is provide the infrastructure in space for satellites to be able to be repaired, and for manufacturing to happen on space stations and whatnot. This will, like I said, help encourage an environment in which companies can think more about reusing and recycling and repairing their satellites, and therefore we can have less space junk, and that's not a good thing. So with our robotic arm, we intend to manufacture. Yeah. Next slide. Yep, so we came up with a solution that's basically a telescoping robotic arm that is able to condense to a smaller form factor. And then once it's in orbit, it's able to extend to a larger footprint and essentially be able to reach out and interface with other nearby satellites. So when we say we want to repair and service other satellites or manufacture stuff in space, we need to actually reach out and interface with these objects. So, and we do that in a variety of ways. We have a lot of different degrees of freedom with our robotic arm that essentially allows it to rotate and move and around other objects. And then what's unique and is novel about our solution is that it's actually telescoping, in that it will extend from roughly about like a 2-foot footprint all the way up to about a 6-foot footprint. And so you could scale that up for larger designs, get a higher ratio of extendability. And basically, we are right now we have an arm that we focus on basically a rotating end effector, so that will essentially, you can put a drill bit on the end, you can drill holes, you can put like some kind of screw on the end of it, so you can start screwing in hardware, or you could even put like some kind of socket adapter that would, basically bolt in bolts. So that's basically the three things that we're looking at right now. However, you could really interface whatever you needed to be on the end of it, whether it be any kind of like sensor suite or some kind of like grabber or anything. All these things would, hopefully we would try to intend to have some kind of modularity. And then basically with this solution, that's going to basically open up all the service and machinability of space, and really contribute to new solutions in space. Next slide.
Okay. With regard to the project engineering timeline, we've maintained a very steady flow in order to keep up to date with our project. In the October of last year, we created our project team and were assigned our mentors. And this is when we started brainstorming our idea of TRAM and the servicing operations that we wanted it to perform. This involved us looking into the actual capabilities of the device and its performance abilities. In November, we worked towards our SRR, or our systems requirements review. And this is when we identify and properly ensure that we are able to continue on with our system design. And you'll be able to notice this later with our trade studies. And then towards the end of the year, we were able to finalize our conceptual CAD design. And then at the beginning of this year, we began our prototype development. And this led us towards the path of PDR, where we provided assurance that our proposed design and manufacturing plans can proceed with minimal risk. Next slide.
Okay, so now I'm going to go a little bit more into the mechanical design of our solution. So basically, we kind of started with, we want something that is able to fold in on itself, be able to rotate. So we actually have our prototype here. We brought here with us today, and essentially it sets up like this, like so. And essentially, it will start in a more collapsed state. So it will be kind of all lower to the ground and all compacted. And then when you're ready to deploy it, essentially it would rotate out like so. And then this rod here would extend out, this one would extend out, and eventually double your footprint reach. We also intended to include a little more joints, like a joint on the bottom, and then have like some kind of swivel action in there, and basically just increase that degrees of freedom. And essentially this works with a lot of servo motors, and they're kind of have a lot of internal housings. And we also retrofitted a lot of linear guardrails that essentially allow it to travel with a lead screw. And so as the lead screw spins, it's able to extend out the telescoping arms. And then as it follows those rails, it keeps it locked together. And essentially that's what's really, rigidifies it and makes sure that it's structurally sound as it reaches out. Yeah, and then basically every single motor has its own little custom mount on the end. Every single, motors up top, motors internally, that all has its own brackets and stuff that is able to keep that all secure. So, yep. Next slide. Okay, and so we also did some preliminary simulations on the tram. Essentially, we kind of just modeled the internal rods, the linear rails on the inside to ensure that, what's our basically our PSI, our yield strength, and what's our bending moments going to look like. So when we simulated the stainless steel rods, we got about like maximum length with the total rods that we bought. We saw there was like about a 5-inch deflection and 50,000 PSI of stress. However, while that PSI was under our yield strength, we saw this was kind of a high number. So we ended up chopping it down to, I think, about a foot on each arm. And so that really mitigated a lot of that stress point. And that's what basically saw minimal deflection. Next slide.
So the tram mission is carried out in 3 distinct phases. The first one is the launch phase. Tram is enclosed within the bosun's locker and will be hosted aboard the port module for launch. And while in flight, Tram performs 3 distinct in-space manufacturing operations critical for orbital assembly. These include drilling, screwing, and bolting. Tram will use its rotating tool holder to identify which tool it is necessary for each operation. Lastly, in Earth, the sensors on in the bosun's locker monitor and record the success of each operation. Data collected will be transmitted through the port module for post-mission analysis. The port module will have enabled us to perform space missions at significantly low cost. Next slide, please.
So this is basically a wiring diagram for the inner mechanism of the arm. So as you can see there, we have like 5-axis stepper motors and 2 stepper motors for the lead screws. So I will just go over the joints and the lead screws. Yeah. So first, our joints, we have like a 1 to 100 gearbox stepper motor at our bottom joint, which is the joint 1. And for our middle joint, we will also be using a 25 to 1 geared stepper motor. And for our third and fourth axis, we will be using like the regular stepper motors to have like a efficient and like non-heat generating operations. For our lead screws, we have 2 stepper motors. They basically drive the main screw to move the arm up and down. And they basically allow it to, as we said, extend its range like 2 times. All of that connects to a main control board, which we'll be showing later. And for the tool wheel, we will be also using a motor to spin that. So when the arm wants to change its tool, it can basically just move over the tool wheel and its arm. I'm sorry, change the tools. Yeah. Next slide. Yeah. Okay, this is our basic wiring diagram for the motor controls. We went with this choice. It is basically an Arduino-based motor controller for the stepper motors. It is a really flexible and like a basic way to like start developing a like a system to connect everything together. This allows us to connect up to like 5 axes, and it also allows us to add extra like preambles to have like more bit types or extra tools that we can add in the future. This can be like go from like a claw at the tip of the arm to like even like a flashlight to light up around the satellite. Yeah, next slide. So this is our control software. It is basically like a real-time way to control the arm. We already designed like a better version from this, which allows us to basically get any data out of the arm live, and it allows us to like do really different things. So one of the things you can do with this is that you can basically make it do predefined motions. So you can have like in-orbit routines for like different purposes, for experiments or different like any utility. And this also allows us to like get live information back onto the ground. So we can like track the position or like any data coming from the system. Yeah. Next slide. Okay. So going to just some notable components. A lot of the components we use are stepper motors, a lead screw kit to give us like linear movement of each segment, and then making sure we have a reliable connection between, or we used a power supply, power cables, and limit switches to make sure we have reliable connectivity between our whole system and between our control software as well. And we were also using, we also wanted to meet the requirement of having good like motion alignment and limited remote commands. And so then we did our trade study essentially based on the inspiration from legacy technologies like the Canadian arm robot on the ISS, automotive robots as well. So we kind of like, we're trying to understand what movement they use, what kind of mechanisms they use. And so we came up with lead screws, belt drive, and a rack and pinion. And so the way we created our criteria was we did it based on the load capacity and the precision, so how well we can control that movement, how reliable it would be in a space environment, and then whether it followed the dimensional constraints of the Bose's logger. And also finally, we want to see how much effort it would take to actually maintain and sustain the mechanism when it was already in orbit. So making sure that it wouldn't, if it's doing a lot of movement, that it wouldn't just wear out itself. And so this led us to going with the lead screws because they met our criteria the best, because we evaluated that it was the best for our actuation because they offered the highest level of control based on the 3 options and the lowest mechanical complexity for the entire arm, and just easier manufacturer reproducibility as well. Next slide.
So as shown here, this is a standard 5x5 likelihood by consequence risk matrix that shows 10 of our risks that range from minor to major risks. That makes this for a project. These risks are correlated with our advanced risk log. Next slide, please. This is our advanced risk log. This again has 10 of our risks ranging from minor to major risks, but I'll go over our 3 high-level criticality risks. One of these risks includes radiation electronic failure, which relates to the possibility of radiation-induced degradation or bit flips caused by extreme high radiation space environments. And this could impact any onboard electronics and cause control systems to lead to mission failure. Prior to mitigation, the likelihood of this risk is a 4 and the consequence is a 5. But our mitigation techniques for this event will include the usage of radiation-hardened components and the addition of shielding, which could then reduce the likelihood to a 2 and the consequence to a 4. Our next 2 high-level risks are involved with the thermal effects in space, such as on our mechanical components, which include arm jamming and thermal failure. Due to the extreme temperature fluctuations in space, there could be a possibility that the mechanical binding and thermal stress may deteriorate, and this impacts both the arms deployment and the structural and electronic components on our board. And this could ultimately lead to a loss of functionality and performance caused by the arm. Prior to mitigation, our likelihood and consequence of these 2 risks are 3 and 5 respectively. But our mitigation techniques for these 2 events, specifically for the arm jamming, include using dry lubricant and precision tolerances. And then for the thermal failure, it includes implementing thermal coatings, insulation, and then ultimately we would conduct a thermal analysis on both components to see how we could ultimately reduce and prevent this risk. And this would also reduce the likelihood and consequences of both of these risks to a 2 and a 5. Next slide, please.
So during the tram development process, we faced many challenges, but at the end of the day, it brought us together as a team and helped deepen our understanding of different engineering disciplines. To start with the concept design, the primary challenge was ensuring the mechanical device fit within the design constraints of the locker. The team worked through multiple design iterations, each member contributing ideas. In the electrical domain, identifying power requirements and motor selection proved challenging. The number of motors, power required to rotate arm and to perform operations required repetitive trial and errors. The team recorded which component configurations most efficiently powered tram. And in the CAD, translating our ideas into a manufacturable model took time. Early CAD models early CAD models would reveal design issues, it was up to the team to step in and help solve these problems. Each iteration helped improve the assembly of tram. Next slide, please.
So in terms of future plans for electrical design, we would try to incorporate a camera or electrical and sensor integration, and this would allow for tram to increase its independency, and it would allow it to increase its operational control as well as object detection. And this step would also include adding sensors to enable the semi-autonomous capability for on-orbit or LEO use, going back to the point of increased functional independency.
Next slide.
Our technical paper provides an in-depth overview of this year's Cosmic Challenge and a detailed background on Arctis's port module, how tram functions, what mechanical electrical components are included, and as well as the software tram uses are thoroughly discussed throughout the paper. Analysis and risks assessments are also included. Next slide, please. Our recommended next steps. Our team has spent countless hours developing tram, and we would like to see it come to life. We will finalize fabricating and integrate the remaining mechanisms. We would also like to finish developing the rotating tool holder, which is essential for enabling tram to operate.
Okay, so tram was developed from a multidisciplinary team of committed undergraduate students. We kind of came together and discovered one solution here to in-space servicing and manufacturing. And we did that a lot with a lot of 3D printing. We did that a lot in SolidWorks and kind of just printing stuff out and testing if it worked. And we learned a lot on, that engineering design process, and also how to, integrate a lot of that components with the electrical side and see where are like the strengths and weaknesses of these servo motors and where is friction going to play a part. And it was a really good project to work on, and we all got to learn a lot. So yeah, it's a great opportunity.
As for the impact of tram, what we hope to be able to change within the industry is that we hope to be able to provide more infrastructure to encourage more reusable and long-term thinking when it comes to satellite manufacturing and how they're deployed. What we hope is that this can decrease costs in the long run to help reduce space debris and make practices more reusable, and overall increase the efficiency of how satellites are deployed and operated. Overall, we hope this can make space more accessible to companies and consumers. As for the lessons we have learned is that I think sustainability is quite frankly a important thing that needs to be strived for. We hope that by providing services such as that this is what is more thought of in the industry. And it also helped taught us the importance of multidisciplinary, of bringing different disciplines together to engage in interdisciplinary work and thinking when it comes to engineering. Next slide.
Next slide. Thank you.
Thank you, guys.
Anybody in the room? I always have questions, so I have a question. Why don't you go first? Okay. All right, yeah, your question go on. So one comment and a question. So on your risk matrix, typically you don't decrease the score of your consequence when you mitigate whatever the risk is. Usually it's just lowering the likelihood. So just to comment on that, it's very rare that you decrease the consequence because it'll always be there no matter what you do. And then question on the sizing of your motors and things. The telescoping idea is really cool. I don't think I've seen that, but I'm not a robotics expert. But It looks like you designed everything for a 1G environment. Did you consider microgravity and how that would, I guess, make you could maybe downsize things or make your motor weaker or something like that?
I can actually answer that. So when we actually first designing this, it was supposed to be much bigger and a lot thinner from this model. But after we started to do the first small versions, we realized that the motors was couldn't handle the gravity, and also the plastic the 3D printed parts we used couldn't handle the the gravity because they start to crack. And we mitigated that by using the rails we used inside, but it still kind of affected this prototype's design.
Yeah, I get it's a prototype, but something to maybe consider. You could maybe use gravity offset something with strings and pulleys so that you could kind of get the best of both worlds. Yeah, go ahead.
All right, I'll have a question and a comment. So my comment is great aspects, and I especially enjoyed the every time you emphasized cross-disciplinary actions because that's a really strong aspect of this competition. One thing I will say is, especially on your conclusion chart, you got to high-minded goals like, hey, this is going to help essentially solve space world hunger. Right? But and that's fine, but you have a specific novelty that you're going after. So make sure you really directly tie what specifically your team is doing to help get to solving space world hunger in that sort of regards. On a more engineering aspect, this is supposed to be loaded in the Bunsen box, and then it's supposed to untelescope out. Yeah. But how does doesn't the box restrict the movement? How do you get around it being in the box? At least according to this, there's one movement and then it goes out. So how do you get around it?
Yep. Yeah, so great question. So there's a couple more capabilities that we were intending to add for future aspects. The first one being is we wanted to fully integrate the base rotating over it. And then also we actually purchased a set of rails, kind of like a drawer, and basically it just kind of slides out and then basically steps outside of the box completely so that it has that more full.
Okay, but that wasn't in your initial design.
No.
Okay.
Yeah. Yeah, just something we didn't get around to integrating it.
All right.
Yeah.
Okay.
Yeah, and I will just add there is this question came up a few times from some of the teams was we asked Noah at Arcasys, it's like, well, can we take off the sides? And his question was, sure, if you want to take off the sides, we can take off the sides. And that's a development project too, and kind of seeing what people are planning to do with it, can help inform them because maybe that was in their plan, maybe it wasn't, but it's something they can work in both on paper and in real life. And any questions online? Okay. I think we have a 15-minute break now before we have the last two briefings of the day.
Good job, guys.
Thank you.
Good job.
Okay, we're just about ready for our next team. The Metal Maniacs.
Yes. Should we wait or should I don't know?
All right, guys. Yeah, go ahead and get started.
Perfect. Hello, Cosmic. Hello, judges.
We are the Missouri University of Science and Technology's Metal Maniacs, and today we're presenting the Lunar Iron Reduction System, or LURS. Next slide. My name is Sunshine Lee. I'm the current Deputy Project Manager, and I would like to give this moment to thank our current advisor and mentor, Dr. Hahn and Brian Newford down the table. Right here. And of course, my incredible team, which we'll hear from shortly. Sorry, you're good. Current NASA and industry interests with investment. Oh, next slide. Sorry. I'm so sorry. We're good. Okay. Future lunar missions have an expansive scope, but require infrastructure and reliable material supply chains to make these demands possible. The Lunar Iron Reduction System is able to not only meet infrastructure needs, but also continuous production and mission requirements for not only NASA, but for other private partners. We're able to do this by not only producing iron in situ material production, but able to not only reduce transport material costs from the Earth, but as well as increase resiliency on the supply chain for lunar and future project use. Our current status is not feasible, which we'll get to in a second. Next slide, please. Sorry. Our current project timeline. As we will present throughout this entire project and this presentation, we'll walk through the exact same examples and revisions of our current prototype from conception to current working and final prototype. Now to April 2025. Next slide, please. These are going to be our system requirements given out by Cosmic and the current C2 track. Typical designated mass and volume and use and power requirements. Next slide, please. And these are internal system requirements of that the prototype shall reduce iron from lunar regolith without the need of a reducing agent. And the prototype shall agglomerate iron into a single workable unit used for consumption or material uses down the further line. Next slide, please. This is our current storyboard of not only how the payload will be transported from the astrobotics, but will be delivered by the Griffin lander on the lunar surface. And thus the LURS system will be able to position itself on the lunar surface to collect, to receive collected lunar regolith, and eventually process that lunar regolith to be used by mission objectives and current future project missions. Next slide, please.
All right. The primary benefits of pursuing iron reduction that we found is that plenty of teams have already looked into aluminum refinement or titanium refinement or pulling other gases from lunar regolith. We wanted to do something that hadn't really been explored too deeply yet. We're aware that I believe 3 years ago, as part of NASA's Big Ideas competition, the University of Utah did manage to get an iron refinement and production system using gases. It's carbonyl gas. It is highly toxic. We were trying to see if there was viability in a process that is simpler and less volatile. The raw iron would be able to be turned into chemistries suitable for casting. You can get structural or habitation creation out of that, or as an initial resource for something like lunar steelmaking. Next slide. We were working off of an oxygen-based reduction method. This was a flawed assumption on my part, where I believed that the very thin lunar atmosphere was predominantly oxygen. It's not, it's hydrogen, which already is a slight failure in regards to our stated goal. Wow, that formatting broke. Of not having a externally supply producing agent. This should show the general process by which you would take hematite, it reduces to magnetite and oxygen, magnetite then reduces to leucite, and oxygen, leucite then reduces to iron and oxygen. Ellingham diagram demonstrates the target temperature we set at, which was 1250 C, with a required partial pressure of oxygen, like 10 to the negative 13th atmospheres, and a required hydrogen partial pressure of 1 atmosphere, which became an issue later on. Next slide.
So the ideal process.
This is a video. You should be able to click in that square.
It says I don't have access.
Really?
Fortunate.
Okay.
Okay, well, from the ideal process, so we initially have a collection arm that will pick up ferrous lunar regolith from the surface of the moon, and we'll deposit it into a collection hopper. This hopper will feed into a crucible, which will then reduce the lunar regolith into workable iron. This iron then will be spit out and will be able to be used by astronauts for various uses. Next slide, please.
Okay, the material feed subsystem, as Jacob explained, first starts with the bulk material being deposited into the primary collection, which serves as the storage reservoir for the incoming feedstock. From there, the auger-based transport system measures an amount of material into the secondary feed hopper. This step is important since it regulates how much material enters the system at the time and helps maintain repeatability between the processing cycles. The feed hopper then delivers the material directly into the crucible, where the thermal processing takes place. Once the material is inside the crucible, a linear actuator applies light compression, which increases the bulk density of the material and improves the particle-to-particle contact, which is critical for enhancing thermal transfer during induction heating. After the heating cycle is complete, the actuator extends to help remove the processed material from the crucible, allowing for the system to reset and begin the next cycle. Next slide.
Next slide.
Okay, the heat reduction subsystem is responsible for generating the thermal energy required for processing. This system uses inductive heating, which works by passing alternating currents through a coil to generate a changing electromagnetic field. That electromagnetic field induces eddy currents, which the conductive materials place inside within the coil. These currents generate heat internally within the material rather than gathering heat from outside of it, allowing for a more direct and efficient energy transfer. Our system is powered by a 12-volt DC supply operating at approximately 65 amps. Although during testing, we were limited to lower effective power levels. The induction coil itself is rated for up to 1 kilowatt of operation and is positioned around the crucible to provide continuous and relatively uniform heating during the processes.
Next slide.
So the electrical control. So the system itself is powered by an Arduino control board with a radio receiver to power remotely. This is all powered by a power management relay and provided will be hardware to communicate with the navigation system. The diagram to the right shows the steps that the power management relay will use to control the system to reduce the iron. Next slide, please. So the electronics board was planned to receive Wi-Fi for short-range communication and radio for mid-range communication. The drive system would be controlled through electronic speed controllers, mainly through relays. Relays would power the induction coil, the linear actuator, and the solar arrays. And we would also have electronical control systems to enable the rover to autonomously navigate destinations or remotely drive through wireless communication. Next slide, please. So the lunar iron reduction system has a total energy consumption of approximately 724 watts. This system stores power in twin lithium iron phosphate batteries, each one rated at approximately 336 watt hours. These will be powered by the Griffin lander solar arrays. This system switches between these batteries regularly to allow cooling, and also having two batteries offers additional redundancy in case of a failure. Below are the requirements breakdown. The induction coil uses the most, approximately kilowatt, and then the rest 20 to 30 watts, approximately. Next slide, please.
Part of this, the system is powered through two sources. There would be an onboard solar array on the processing unit itself, and then also power would ideally be taken from the Griffin lander in order to meet those requirements.
Navigation. So the movement is powered by 4 motor-driven wheels. These will be primarily used to get it off of the Griffin lander and also move around a little bit. They're designed for short-range traversal on relatively flat terrain. The primary function is to position the system for optimal material intake. And like I said before, they're equipped with medium to short-range communication array for remote operation. Next slide, please.
So the innovation in our design was that the LERS was one of the first things to look at iron reduction systems. And most of the existing methods required consumable materials such as like graphite rods or consumable reduction gases. Our thing would have required no reducing agent, meaning it wouldn't have any limiting factor other than the degradation over time of the system, damage to it over time. Removing any reduction agents would increase the chemical simplicity of the system, but didn't quite work out that way. And the provided iron for future lunar missions would be able to be used for tools and infrastructure and whatever it needed to be used for. Next slide, please. So our first revision was a rover. It would collect the material off the surface using a magnet, and it would collect it in a hopper there. First system would have a onboard processing system. It would be 1 unit. Later, we moved on to it having 2 separate units, being the rover and the processing system. And later, we completely excluded the rover to just focus on the processing unit. As said before, it would be connected through Wi-Fi and radio communication, and it'd be fully autonomous on its own. Next slide, please. So yeah, the limitations here, it was just really overambitious to have a rover as well as a processing system all in one. Focusing just on the processing system would greatly simplify our job. We'd have way too much power consumption having to run the rover as well as the processing unit. We'd only really have to be able to use one at a time. So it would have to stop somewhere and start its reduction process. And that's just inefficient. And thermal regulation would be a problem over time. You don't want to get the rover way too hot if there's not proper thermal management. Next slide, please. Okay. So here is our more official final processing unit. We have a whole lot more here. Sorry, I'm blanking. We've got ourselves a handmade high fire clay fired at cone 10 to act as the crucible. We have our frame made out of 80-20 to be modular and work better as a prototype. We have ourselves all our electronics attached on there. I added on a mock radiator, though it wasn't sized to be properly sized. We hadn't determined that. Mostly we're focusing on modularity and easy to modify design. Next slide, please. So yeah, our limitations was most iron on the surface of the moon is just bound in olivines and pyroxenes. They're very hard to get at. That's just beyond the scope. So anything that we'd be putting into the system would have to be pre-processed by another collection system that would probably already be collecting titanium and aluminum powders. We have really no way to access pure iron oxide feedstock to be put into this. Environmental constraints, no oxygen in the atmosphere. Well, yeah, inhibits the reduction. We didn't have any way to really test this system because we didn't have access to a very high vacuum or any way to displace oxygen. And our prototype didn't really reach the temperatures required. We only reached about 400 degrees Celsius, where the minimum to see anything happen would be 700 degrees Celsius. And we couldn't accurately measure the temperature of the feedstock because our infrared thermometers were giving us all kinds of different numbers. Next slide, please.
Revision 3 is what we ultimately ended up making for our prototype. We were unfortunately unable to bring it here, although we're relatively certain it would have some issues getting past security, as it looks a little suspicious. You can see the 80/20 frame, the collection hopper. There should be another image on the following slide that shows the auger in place, the feed hopper. You can see the induction coil assembly, which we purchased and slightly modified. In general, this is representing our shift from a focus on an all-in-one system with a rover that also did collection to just the processing system to a slightly scaled down version suitable for testing in Earth conditions, because we found we were unable to replicate anything approximating lunar conditions. We had a myriad of quote-unquote upgrades to this system over time. We self-wound a 20-turn copper coil out of 4-gauge tube. We increased the wire gauge from 12 to 4 because we believed that it could have been a current limiting factor. We upgraded a relay from a 10 amp to an 80 amp solid state relay. And the general focus shifted from taking any kind of regolith simulant and trying to get the iron out of it because of the very, very low iron concentrations found in the highland areas where the Artemis missions are forecasted to land, to not necessarily assuming, but assuming that some other system would be capable of locating and transporting iron oxides to the processing unit. To it, we got iron powder, magnetite powder mixing together in a fixed ratio and heated to undergo a paratectoid transformation to woostite above a certain temperature. That was our source for where our primary reduced iron oxide is coming from, since woostite was not really able to be liberated from the regolith as it is bound within pyroxenes and olivines in a way that is chemically complex to try to get out. Next slide. Experienced limitations with our prototype. Ultimately, during maintenance, an electrical short from the wire damaged critical componentry inside the power supply, which resulted in a failure to complete the testing regimen that we had set out to do. The 20-turn coil did not increase efficiency. This is probably due to the spacing between the coils not being consistent. It was hand wound. It was quite rough. Ultimately, we observed that it had a much slower heating rate and achieved lower peak temperatures of only around 200 degrees Celsius after 35 minutes, where the heating rate had largely plateaued. And it was unclear if changing the relay out really had any impact. It seemed to dissipate heat better, but it didn't seem to really change how much current was being delivered to the coil. We did find out that this is because the board that we were using to control the coil is actually only rated for 20 amps. So we were feeding it 65, supposedly, and thus it only would have been able to generate around 240 watts of power, or would have only been able to use 240 watts of power. And it seems that if it's only about a quarter as effective as it should be, our arrangement probably would have worked with an adequate power supply. Next slide. Our experimental design, we would load woostite or pre-woostite, the mixed metal oxide charged material, into the crucible. It would be compressed lightly. Heating in an induction coil. This one was actually provided by the university for testing, which was very kind of them. We monitored the surface sample temperature with an IR thermometer with moderate accuracy. we intended to heat the sample until the soak temperature was reached and then hold it for an amount of time until some amount of reduction had occurred. The original testing regimen had various time frames to determine how much had occurred, if we could get a relative rate and such. Due to both the damage to the system and a general lack of time going into the past couple of weeks, we were unable to complete this testing regimen. After reduction is completed, if sintering had not already occurred by being held in elevated temperature, we would continue heating until such had been observed, and then remove the sample, analyze it. If possible, we were not able to arrange this within the time frame, but use XRD to determine whether we actually did end up forming lucite, as it's essentially the only optical technique that will let you determine individual phase formations. Next slide. And the general results of our tests. That image is a little washed out, but it shows the top is the initial charge material and the bottom is the post-testing material. The bottom is distinctly redder, which we believe indicates that the temperature did get high enough for some form of oxidation to actually take place, where that mixed metal oxide formed hematite in some capacity. But in general, the samples never really reached our soak temperature of 1250 C. There were limitations of the coil assembly that we made. We believe that the grain size of the powders we mixed was too small, actually, that it caused interference with the induction and reduced its heating efficiency. And we determined that neither reduction or agglomeration occurred. We don't expect any lucite was formed by reduction, and oxidation may have occurred. Next slide. General feasibility. We've determined that the process that we have created is not feasible for it. It's trying to do non-carbothermal, non-external gaseous reduction, which should have kind of been a tip off earlier on that there would be several issues with our plan. And then this is another review of the things that went wrong, frankly. Next slide.
So our current path to PDR, if it's not obvious already, is current retesting not only our concept and our assumptions made,
but also redesign of our power architecture, including the coil and power control, but also selecting feedstock that is demonstrably compatible with our current system and our goals. And the next step of this path to PDR is obviously to retest or revision prototype version 4 and its multiple iterations that are probably going to come afterwards, and hopefully test within something similar to lunar conditions and the environment. Next slide, please.
There were some technical gaps in areas that limited the feasibility of our system. They helped us identify the areas for future development. One of the main challenges were the gases reducing agents such as hydrogen. Effective iron reduction requires a controlled environment, but our system lacked a sealed reaction chamber that is capable of maintaining the necessary pressure and gas composition. Closely related to this is the issue of hydrogen and collection and reclamation. In a lunar environment, hydrogen would be a valuable and limited resource, so any valuable system would need a way to capture, recycle, and reuse it efficiently. This capability was beyond the scope of our prototype.
Next slide, please.
Our biggest challenges were our overconfidence in the beginning of our design process. We didn't significantly question our initial assumptions or seek enough thought through external feedback, which led to us spending a considerable amount of time pursuing approaches that were not viable, which resulted in a lot of inefficiencies and loss of development time.
We also saw the multiple current technical problems of voltage,
insufficient grain size, and inability to heat
our clay crucibles, but also team management and organization due to multiple restructurings and current time and resources and delays of our current prototype just led overall to like our current prototype not being really tested on time and let alone being feasible. Next slide, please.
We had aimed to try to break a little bit new ground by showing that we could synthesize our own iron oxides for reduction, that we weren't necessarily just trying to seek them from the lunar environment. We are still using bulk lunar resources. One source for this, magnetite, is found in the form of ejecta, and nanophase iron has been identified, which could be collected and used as part of that mixed metal oxide powder. We looked into using microwaves or other heating sources as alternatives. They were proposed but dismissed due to complexity and potential danger with using those methods. There's also pyrolysis, which is straight thermal decomposition instead of necessarily reduction. It's been explored with other forms of heating, confocal lens light, targeted laser heating, plasma heating. Again, proposed, dismissed due to complexity and cost to try to make a functioning prototype. Next slide.
Any questions?
Here now for questions. Assume there will be plenty.
My first time.
Go ahead. Sure. Yes.
Yeah, we have time for questions.
Oh, perfect.
All right. I'll do a question, comment and a question. So, if anything, this presentation showed how you rolled with the punches when wrong. You understood how you could basically overcome them, whether it was physical ones that you actually tested or actual the physical presentation that you were trying to go after. So, good job in trying to overcome that. And at least when you said, "Hey, there was an idea that we couldn't exactly prove," proving the null hypothesis is always good. So, just because something doesn't work doesn't mean you get good information from it. So that's very good from that perspective. More so from an engineering perspective, since this is planned to be a lunar payload, and there's a lot of thermal aspects that are involved in this, is this being designated for the near side of the moon, the far side of the moon? Where do you plan to place this? Because those are two distinctly different areas with two distinctive thermal environments.
Right. So
if you don't know, that's fine.
We've using a thermal map of the moon, which has been provided by NASA through their website. I unfortunately don't have a strong citation to look at. We determined that the temperature swings observed probably or aren't likely to cause damage to the components even under operation, just because the radiative heat from the coil is fairly small compared to the actual applied heat to the sample. If needed, we can obviously implement more thermal shielding, reflective coatings, or just greater insulation around the unit. It is something that was considered but was not deemed an issue for the prototyping itself. All right.
I mentored the team, so it's probably not good at
I see.
questions and
Fair
stuff.
enough.
So, but is there any other questions online
Is there something in the chat?
or in the chat? No, that's
Oh, just 2 minutes. Thank you, Jacob.
Yeah, I would just say that I think sometimes it's hard to look at the hard work you've done and say, well, this isn't going to work, or this is a bad idea, right? But sometimes that's the most important step. So I think it's good. You learn more you often learn more from failure than from success. So just take that away. And the other thing I said, I've published several papers which were, this didn't work, right? And I published it, and I've had people come up to me says, oh yeah, like we tried that too and it didn't work. I'm like, man, I wish you would share that. Now, this may not be an example of where you need to do that. Like the information might have already been out there, but if you're doing original research, a negative result is still valuable, right? That's all. Any other questions before we give a couple minutes for the judges to record scores? Okay, so we'll hold for 2 minutes, and then the Kennesaw State team will close us out for the day. Deep Interstellar Solutions. Thanks, guys. Good job. Oh yeah, I forgot to ask the obvious questions. Is how did you get all the way there from Missouri?
So
Sure, go ahead.
we walked.
Sunshine and Alicia flew. Myself, Evan, and Jacob drove the 17 hours and had a mechanical failure about 700 miles in.
Oh, geez. You guys deserve an award just for that.
We should have taken the plane.
Your commendation is appreciated. We will drive another 17 hours back.
Or fly.
My car's in Florida, so no, we aren't.
Ship the car.
Nope. Nope. Nope.
Hey, you guys can go ahead.
We're ready to go, Dr. Rowe?
Yep, go ahead. You're all
Okay. Can we go back to our intro slide? I'm sorry. Is there not a slide before that?
I don't.
I do not see one, no.
Oh, okay. Well, we're sorry about that. I'll just go ahead and get going. We are Deep Interstellar Solutions from Kennesaw State University. Today, we are going to be presenting ORCA. So I am Max Starnes, the project manager. Today, our co-leader, Keegan Jordan, is going to be giving the body of our presentation, but you'll hear from me in just a little while. So Keegan, take it away.
All right. Thank you, Max. So like Max said, we are Deep Interstellar Solutions from Kennesaw State University. All 5 of us here are pursuing a bachelor's in mechanical engineering with a minor in aerospace engineering. So starting at the top left, I will introduce you to everybody. Top left, you'll see our leader and project manager, Max Starnes. And then beside him, you will see me, Keegan Jordan. I am the co-leader and simulation expert. And then we have Ian Griffith, the FEA expert, Grant Pesquiera, our engineering expert, and Vishal Patel, our report and presentation expert. Next slide, please. We have divided this presentation into 7 sections, and we're going to be getting started with our executive summary. Next slide, please. Next slide, one more time. For the Cosmic Challenge, our team chose to pursue track 1, which is to design a multi-step manufacturing line that fits within the confines of a bosun's locker. At the beginning of this competition and this project, we got together as a team and we were discussing, like, what do we want to manufacture? Like, what product would be useful for on-demand low Earth orbit manufacturing? What product would be needed to help service current technology and also help rapid prototype future technology while in orbit? And what we settled on was printed circuit boards, PCBs. PCBs play an important role in all technology nowadays. They serve as the backbone for all electronics, and if they get damaged, the entire assembly will fail. So it is our team's belief that the ability to manufacture these on demand would promote ISAM and independence from Earth. Next slide, please. Moving into our mission concept. Next slide, please. Our motivation behind this project is on-demand PCB manufacturing in space. This would provide autonomy, adaptability, and efficiency for current orbital operations, and it is a critical step towards sustainable deep space exploration. This would allow astronauts and engineers to design, adapt, and produce custom electronics tailored to their needs. Next slide, please. The problem that we are facing is that we are currently too reliant on Earth-based manufacturing. PCBs are essential components. If a board fails, though, a replacement must be launched from Earth, which is very costly and very slow. Our team believes that a sustained presence outside of Earth cannot rely on Earth-based manufacturing alone. So developing and demonstrating this process to manufacture PCBs is an important, currently absent step towards that long-term goal of human exploration of space. Next slide, please. So now that we have identified our goal, we are, let's get there. So we've broken the process of the manufacturing line up into 3 steps. And those are, next slide, please, storage. That is storage of the raw materials, pre-processing and post-processing. Next slide, please. Manufacturing of the PCB itself. Next slide, please. And the verification of the PCB. Next slide, please. We then laid out the framework of how we would approach this project to meet our goals and our objectives. Our first step was just to identify what operations our manufacturing line should include. And then from there, our second step was designing that system. Step 3 was modeling that system, and step 4 was our validation and verification to ensure accurate and repeatable results. Next slide, please. Here's our management plan. Oh, wow, that did not translate well. Here's our management plan. It was formatted differently. We divided our team into 4 distinct divisions to facilitate the success of this project. So Max Starnes, he headed up our project management division. Grant and I, we did our assembly and design division. Vishal was our risk assessment and mitigation. And Ian was our engineering and simulation division. Next slide, please. Here is our timeline for our project. As you can see, we finished this back in December. We are a single semester capstone course at Kennesaw State for the aerospace minor. So we had to focus, and we successfully completed all the requirements within that 1 semester. Next slide, please. Moving on to our system requirement review. We're going to start with our system requirements. Next slide, please. So for our system requirements, the goal of this experiment is to manufacture 10 PCBs before the system needs to be refilled. And then we're also operating within the constraints of a bosun's locker. Next slide, please. For our functional requirements, we want to be able to store 10 PCB blanks, complete all the needed operations on that copper, and then store the completed board in storage. Next slide, please. For our environmental requirements, we want to ensure the system can operate in a low Earth orbit environment. Next slide, please. Our manufacturing requirements, we want to make the system adaptable, including 60% commercial off-the-shelf components and 3 degrees of freedom. Next slide, please. For our design requirements, we wanted to make the system be cost-effective and meet the constraints of the bosun's locker and the launch requirements of our thesis. Next slide, please. Continuing design requirements, we also are designing the system to be accurate and repeatable. Next slide, please. Our operational success requirements, these are our measures of success, and they helped inform our design criteria. Next, please. And then finally, our data handling and comms requirement. We want the system to be able to receive commands remotely. Next. So moving on to our conceptual design review. Next, please. So using the list of requirements from our system requirement review, we managed to derive these 7 criteria with their parameter to model our project around. So we wanted the device to be, simple as possible. We wanted it to be autonomous with no more than 2 human interactions. We used the specifications of the bosun's locker to define the swap parameters. Price, we wanted to be less than $20,000. Manufacturability, that's the ease of manufacturing of the PCB, the PCB board, and also of the assembly or the manufacturing line itself. We wanted the design to be durable and adaptable in the sense that it contains 60% commercial off-the-shelf components and 3 degrees of freedom. Next slide, please. So as a team, we performed a weighted matrix to determine the levels of importance of each of these design criteria. Next, please. We then created and ranked each design. So between our group, we managed to create 6 unique designs. We then compared each of those designs against the design metrics using a scale ranging from -3, which is significantly worse than the requirement, to +3, which is significantly better than the requirement, to determine the best performing design. Next slide, please. So we will start moving into our conceptual designs. So design 1, this design utilized a PEZ dispenser-like method for dispensing and storing the PCB boards. It also contained a laser etcher that etched the traces onto the copper. Next slide, please. Design number 2. This design used a series of roller pins to translate the PCB board to and from storage. Next slide, please. Design 3. This design mimicked the process of how hobbyists make PCB boards from home with the etching film and the UV curing light. Next slide, please. Design 4 uses an elevator and an accordion type translation system to move the PCBs to and from the work area. Next slide, please. And design 5 utilized a system to remove debris from the work area. Next slide, please. Finally, we have conceptual design 6. This is a modular system where each step of the manufacturing process has a designated area of operation. Next slide, please. And so after applying each design against the decision matrix, design 6 was found to be the easy winner of the group with a score of +195. Next slide, please. And here we have a rendering of what that design would look like inside a bosun's locker. Next slide, please. So we'll now be moving into our preliminary design review, starting with our concept of ops. I'm going to hand that over to Max Starnes so he can talk about the function during normal operations. So go ahead, Max.
All right, thank you, Keegan. If you would go to the next slide.
Here, the magazine of PCB blanks and their holding trays are lowered to meet the conveyor, where the first plate attaches to the conveyor before the elevator moves the remaining blanks back to storage. Next, the blank is transported to the etching station, where the initial circuitry is etched into the copper of the blank. During this process, the debris management system is expelling any particulates from the work area using inert gas. In this next step, the solder mask film is applied and cured to the blank, before it is transported back to the etching station to remove the masking from the connection pads. Finally, the PCB is transported to the secondary storage magazine, where the elevator system comes down and lifts the now complete board into storage.
All right, thank you very much. If you would go to the next slide, and we're going to give it back to Keegan.
Thank you, Max. So with that concept developed, we then performed engineering analysis and trade studies on all of the components that make up that design. It ended up being about 40 slides worth of briefing though. So in order to truncate that and make our time for this presentation, we're only going to be highlighting 3. They were the most interesting to us. So if you'll go to the next slide, please. We'll be starting with the frame assembly. Next slide, please. So the frame of the system are the pieces outlined in the red color on the rightmost picture. For our static and thermal analyses, we wanted to simulate the components in what we deemed are the worst case scenario conditions. And these conditions are forces from Earth's gravity, full shadow and direct sunlight temperature conditions. And then we also assumed that the support poles were under load from the weight of the top panel. Next slide, please. Here are the results of that simulation. Let me take a second to walk you through how these plots are formatted. So the plots are divided into 3 columns. The leftmost column shows the principal stress. The middle is our equivalent displacement, and the rightmost is our equivalent strain. Then the top row is the components that were subjected to the direct sunlight condition of 394 Kelvin. And the bottom row is the components subjected to full shadow conditions of 148.15 Kelvin. So from this simulation, the results showed that we had a max principal stress of 3.1 megapascals, a max displacement of 1.13 millimeters, and a max strain of 30.2 micrometers over millimeter. And those were all during the full shadow conditions. Next slide, please. For the trade studies on the frame, we looked at a few different material types, but ultimately settled on aluminum 6061-T6 because it is robust, relatively cheap, lightweight, and it achieved the required behavior under the simulation conditions. Next slide, please. Our next trade study and analysis is going to be the conveyor assembly, starting with the chain. Next slide. We chose a chain in sprocket assembly versus some other solutions because the chain and sprocket assembly has been tried and tested in low Earth orbit environments in the past with the SpaceX Starship Pez dispensers and of course, other applications as well. And we wanted to keep as much of that environment tested technology as we could. The worst case scenario assumptions for the chain were forces due to Earth's gravity, and the chain is under load of all 10 PCB trays with the blanks loaded in them. Next slide, please. For the chain, we opted to perform the analysis using hand calcs. We used a gear and chain analysis to determine what forces we would need to overcome, or we would be enduring, I guess you'd say. We found that the tight side tension, T1, would be 60 newtons. The slack side tension, T2, would be 10 newtons, and the required motor torque is 0.92 Newton meters. Next slide, please. We then took this data to find the components that would be best suited for our application. We ultimately selected the IWIS 06B-1 chain due to its high reliability and strength. Next slide, please. Similarly, for the stepper motors that would be driving the chain and sprocket assembly, we used the results of that gear and chain analysis to make an informed decision for our trade study. Next slide, please. The stepper motor we ended up deciding on was the 5-space 52-2 NEMA. They achieve very precise motion, and they are actually designed for use in low Earth orbit environments. Next slide, please. The final analysis we'll look at is the tool head assembly. Next slide, please. So these are the components that will be laser etching the traces into the copper and then also expelling the debris away from the working area. The assumptions we made for our static and thermal simulations were Earth's gravity, full shadow, and direct sunlight once again. Next slide, please. The results of these simulations, they showed non-factor stress, displacement, and strain for the tool head assembly itself. Next slide, please. For the trade study on the laser etching portion of the tool head, we looked at laser etchers that were marketed towards etching metals. Since laser etching in microgravity is sort of a new concept, and with our sizing constraints, our biggest concern when shopping for one was power requirements. With that in mind, we ended up settling on this Elegoo Fecta because it met the power requirements that we had, and it was also most cost effective. Next slide, please. With the removal of material that comes with laser etching, we ultimately knew that we need to find a solution for the debris. We were concerned that the debris would inevitably cause damage to its surrounding components. So to mitigate this, we investigated a few different methods of debris expulsion, and we ultimately settled on a inert gas purge. It was the most simplistic and most widely used method for debris expulsion. Next slide, please. After performing all of these analyses and trade studies, we made a mass, cost, and power analysis. Next slide, please. So we took all the components and we got their dedicated values, and then we put them in a chart. Will you go to the next slide, please? Looking closer at the mass analysis, we have a 62% margin on mass compared to the system requirement. In future iterations, we may look for opportunities to add other experiments that aren't included in this current design. Next slide, please. For the power analysis, the peak power of the design is 281 watts, and you can see that is from the frame and power screw system. Since we designed this system to run in a sequential fashion, only one of these systems will be running at one time, which means that it keeps us below the 300-watt operating power requirement. So while at peak power, we do have a 6% margin. So that means we do have a small room for fluctuations in power consumption. Next slide, please. Comparing our design costs with our original design requirement of 20,000, we have an 80% margin, 87% margin. This does not include fabrication cost of our custom components. So in this section will need to be further refined in future iterations to include that and other associated costs that weren't accounted for. Next slide, please. All right, moving on to our NASA TRL. The team looked at each of these subsystems in the overall design and tried to identify and indicate where they fell on the NASA TRL spectrum. Next slide, please. For the risk assessment, the team looked at the system as a whole and identified possible failure points, the criticality associated with that failure, and a plan to mitigate them. I'm going to highlight just the top three highest critical ones, being the laser beam path deviation, which we will mitigate with redundant sensors, solder mask adhesion failure, we're going to mitigate with adjustable settings and a visual verification, and the debris management risk that will be mitigated by employing a localized jet of nitrogen and a shroud to collect the particulates. Next slide, please. Okay, the fun part. So moving on, this is going to be our innovative concepts. Next slide, please. So our first innovative concept is the debris collection, expulsion, and collection system. This introduces a proven vacuum expulsion method into a confined space to effectively collect debris. Next slide, please. Our second innovative concept is thermal printed solder mask. So due to solder masking usually requiring the use of liquids and gravitational pull, we developed a solution which combined the dry film and thermal printing to create a new process to apply a solder mask designed specifically for low Earth orbit applications. Next slide, please. Our third innovative concept, the Orca utilizes a laser etching machine to trace the circuitry into the copper. This is a yet unused method of PCB manufacturing in an untested operational environment. Next slide, please. In order for Orca to work in the way that we've intended it, we need further research into how laser etchers behave in vacuum environments. We also need to look a little deeper in how a debris expulsion system would behave in a confined space. And we need to experiment with methods to prevent off-gassing when etching the copper. Next slide, please. Some design challenges that we faced along the way, the temperature difference in low Earth orbit played a major role in a lot of design changes. We also faced some challenges finding separ motors that fit our needed requirement. And of course, our innovative concept posed their own unique challenges. Next slide, please. Skills gained. We gained so many skills, but specifically, we got to work as a team, so we developed teamwork skills. We all got to play around on SolidWorks, so we learned simulation and modeling, presentation skills, public speaking. My personal favorite is that we got to learn the process of systems engineering from start to finish. So yeah, next slide, please. We are in conclusion, next slide, please. In conclusion, our team, Deep Interstellar Solution, believes that we have theoretically accomplished the goal of manufacturing PCBs in orbit. We believe that this application has the potential to serve as a stepping stone for future ISAM projects, whether for rapid repairs or rapid prototyping new technology. Next slide, please. Key accomplishments. The main key accomplishment from our team is that we've met or exceeded the design requirements set by the team and by the Cosmic Challenge. Next slide, please. Project impact. Our team believes that Orca will impact the aerospace industry in a multitude of ways. It will reduce the reliance on Earth-based manufacturing and promote innovation by allowing the crew to rapid prototype circuit boards to fit their use case. Next slide, please. We hope that students in the future will be able to use Orca as a stepping stone for their own ISAM projects. Orca has impacted us as well by teaching us many new skills and giving us an introduction to the aerospace industry. And it also got us first place at the KSU Fall 2025 Capstone Symposium. So next slide, please. Some recommendations that we have. We recommend in-lab testing and in-environment testing to evaluate the effects of that thermal stress and microgravity on a precise system such as this. Next slide, please. In future iterations, we would like to dive a little deeper into the validation of the PCBs and safeguarding of the system. Next slide, please. We would also like to take a moment to thank our professor, Dr. Vijay Goyal, and our mentor, Matt Anderson, for their guidance and assistance along the way. And huge congratulations to our mentor, Matt, for winning the Cosmic Mentor of the Year Award. They were both very invaluable resource to our team. So thank you. Next slide, please. And one more. Any questions?
Okay. Do we have questions?
Jacob, always know I have a question.
Go ahead, Crispy.
So, comment and a question first. With your presentation, great job. It was very clean. I think one of the favorite aspects I have is that you kept on bringing up the agenda just because it kept the main theme kind of going, which is always good. The technical question I have is on one of your charts, you showed that you had, I don't know, your mass was extremely low in that sort of case, right? And so when you have extra mass, there's always the want to do more because then you have the ability to stick more into it to go after science. If you have extra mass, what would be kind of an extension that you would want to add to this?
Yeah, so, I'm sorry.
Do you want to take it or do you want me to?
You take it, Max. You got it.
Okay. I think one of the things that we really wanted to focus on more is that we weren't able to include, of course, mass for the actual controller system for the device. Also, if we could add another system, we would really like to have a way to drill into the PCB boards, as most components use a through system whenever you're soldering. On top of that, we would also really like to develop our nitrogen purging system a little bit more, and that would definitely add some more weight. So really, if we could just refine what we already have, we would be very happy. But if we had to add something new, one concept that we really wanted to try and do, but we just didn't have time, was to actually have a system to test the circuit boards themselves. So it would be kind of like a multimeter, but it would come down and it would be automated.
And this is not meant to say if you always have extra mass, add something, but in space, if you have extra mass, there's always the question of you do more.
Right.
Do you have any other questions in the room or online? So I'll ask a question because it's like, let's say we said, okay, you're gonna do this. You guys are gonna design and build this thing. You have one risk reduction test you can do in microgravity. What are you testing?
Keegan, do you want to take this one?
Yeah, I'm sorry, Jacob. Could you repeat that last part one more time?
So basically, if someone like put you on contract to build this, right, and they
Yes.
want to fly in 4 years or whatever, but they said, hey, we have an opportunity in 12 months to do an experiment in microgravity to do some risk reduction. What is the experiment you would want to do?
Oh, yeah. I would definitely say the well, there's a few. Probably the laser etching in a vacuum. We definitely want to make sure that it's not going to have any side effects, because I don't think there's ever been a laser etching in low Earth orbit before, has there? So, but definitely that.
Not that we're aware of, or that we could find any research into. And one of the main factors that would play into that as well is we are using a sorry, I'm looking at Mr. Anderson's response. We're using copper plates, which are inherently reflective. So whenever you have a laser and a reflective surface, you're gonna have reflections that go places you don't want them to go. And that would probably be one of the things that we want to kind of focus on in initial testing, is making sure that those laser beams don't go anywhere that's going to affect the system as a whole.
Okay, great. Yeah. The other question wasn't the question was they finished in one semester. So yes, and I also was very impressed with how much you guys got done in one semester. And we are at time for the day. So I want to thank you guys. I think you did a great job. I think all these teams did a great job. And yeah, and I know we've already started picking your brain, and Matt and VJ, it's like, okay, how can we, is a one semester thing a one-off, or are there guidelines we can give? Because I know one of the difference with your team is VJ had you hit the ground running on day one. I don't know how you could do it in one semester otherwise, but great job. Thank you, everyone. Brian, I'm going to turn it over to you if you have any parting words.
Brian had to step out, so
good job to the teams.
Good job to the team.
Okay.
Well, thank you all for the opportunity to present. We really enjoyed the challenge and the experience.
Yeah.
Yeah, and that is a wrap for today. We're back tomorrow, one more day. We're gonna take the roadshow to Goddard Space Flight Center. I think there are 7 teams going there tomorrow, so that'll be the biggest crowd we get. And yeah, I hope you all like keep pushing. There's some great ideas here, and I think that's it. And if anyone was in the room, was acting as a judge and has score sheets, just turn those into Brian, or take a photo of them and send them to me, so I can collect the scores and keep going with that. All right, thanks everyone.
I'll send you my scores probably tomorrow morning. I need to drive back, so thank you.
All right, thank you.